Hello students, welcome to the class. Sorry for the delay. So today is our day 20 of this JEE 40 days crash course and we will start with a new chapter, that is classification of elements and periodicity in properties. Although this chapter is a small one, but you will see that marks are asked from this question. Okay, you can see questions from this chapter in various years. So this is our disclaimer. And if we look upon the analysis of this chapter, then you can see that there is a weight percentage of 3.7 coming from this chapter, and at least one question is always present there from the chapter classification of elements, right? If I talk about the important topics, then you will see questions mostly from the modern periodic law and from the periodic trends. So these are the two important parts where you will see questions from, and you will not see questions from the older versions of the periodic table. So that is something which is not important for your exam. You will see mostly from the modern periodic trend and from the physical and chemical properties regarding its trends in the periodic table. So you can see that in every year there is one question from this periodic trend. Now what we will study today, so this will be the day that we will cover this chapter in the whole sense. Okay, so we will not do it in two parts unlike other chapters. First of all, only we will address the names whose attempts were made to classify the elements. Then after, we will move on to directly this modern periodic law and the present form of periodic table. Then we will see the classification of elements based on the groups and periods. So elements can be divided into groups and periods and they are named accordingly. And lastly, we will look upon the trends that are observed in the particular groups or periods. So starting with the first one, which is historical development of periodic table. So where there were many attempts made to classify the elements by different scientists. First of all, we have Proud's hypothesis. Then we have Dauvergne. So this was the most important one. He arranged the element into a group of triads and observed that the atomic mass of the middle element was approximately equals to the average of the other two. For example, lithium, sodium, potassium. The average mass of lithium and potassium was close to the mass of sodium. However, this trick only worked for a few elements. Then come the Newland's law of octaves. So in 1864, he arranged elements according to their increasing atomic mass. He noticed that properties of every eighth element were similar to the first. Just like in music we have sa re ga ma pa dha ni sa, he called this as law of octaves. However, this law was only valid up to calcium. After that, everything failed. Then after we have Lothar Meyer atomic volume. Again, he plotted various physical properties against the atomic weight. And then he observed that there was repetition in the properties of elements both in the physical and chemical sense. And Mendeleev also took the same atomic weight for doing the classification. So in 1869, this was the last attempt before the advent of the modern periodic table. Okay, so in 1869, he finally created an excellent periodic table. He arranged elements in the order of their atomic mass. In this table, he also left empty spaces for elements that had not yet been discovered and predicted their properties as well. So this was something which was very magnificent. To a large extent, his table is the basis of today's periodic table, but the modern periodic table is totally based upon the atomic number and not on the atomic mass. Lastly, we have this modern periodic table. This is the table form that we see today in our day-to-day life. Here, the properties of the element are considered to be periodic function of their atomic weights, atomic number rather than their atomic weights. And this is the basis of the modern periodic table. And this statement that I have told right now, which is properties of elements are the periodic function of their atomic number, is the modern periodic law. Now, this was given by Henry Moseley. This modern periodic law was given by Henry Moseley. So what did he did? he showed that atomic number is a fundamental property of any element and not its atomic mass or weight. He formulated the modern periodic law on this basis. Now, what does this mean? Sir Dmitry Mendeleev had also classified elements, but in his classification, he considered atomic weight or atomic mass as the fundamental property, and that was his mistake. However, Henry Moseley took atomic number instead of atomic mass, and this idea turned out to be very genius. Because of this, he formulated the modern periodic law. Now, why did he take this atomic number? Because if you see any chemical properties, there we can only observe chemical reactions because of the exchange of an electrons. And electrons is something which is closely related to atomic number and not atomic mass. Therefore, the properties are also closely related to the atomic number and not the atomic mass. Next, what was the modern periodic law? So here you can just write it down. It's very important. It states that physical and chemical properties both of any element are the periodic functions of atomic number. Now, what is the meaning of periodic function? You will see that after a certain interval of atomic number, there is a repetition of property. So for this repetition term, we have this periodic term. And since this repetition is proper for a proper function, so we name it as periodic function. Okay. So what we have concluded, that your atomic number are repeated, means the physical and chemical properties are repeated based on their atomic number, and hence we call this atomic number as the periodic functions of their properties. Moving on to the next, this modern periodic table is also known as the Bohr's periodic table. Now, why it is called so? So it is just a graphical representation of the principle given above. So what was that principle above? Basically, it was about how your atomic orbital fill up based on their energy. Next, what has been done in this table is that he arranged the element in the increasing order of their atomic number, and in this way he formulated the modern periodic table. Now, the drawback of the Dmitry Mendeleev's periodic table was that he could not address isotopes. Okay, since he was taking atomic mass, therefore, for the same element, if there are two isotopes, then in the periodic table, according to Dmitry Mendeleev, it should have two positions, but it is not seen in his periodic table. Whereas if we take the atomic number, then it would not be necessary for the isotopes to be placed in two different positions, because isotopes have same atomic number. Next, now let us talk about the characteristics of this table. So write it down, it is very important. First one, it has 7 periods and 18 groups. We will see this in an image in the next slide. So we will see what period means and what group means, and what the sub-concept of subgroups A and B has now been removed. Now groups are numbered from 1 to 18. Earlier A and B was used. Okay. And period starts from 1 and moved on to 7. As simple as the counting. Groups are numbered in the same way, starting from 1 to 18 rather than group A or group B. Similarly, periods are numbered from 1 to 7. So how many groups are there? 18 groups and 7 periods. How can we visualize it? So let us look upon a table here. What you can see here is the period on the left column. 1, 2, 3, 4, 5, 6, 7. Or if you look upon the groups here, this is group number 1, group number 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 and 18. And we have also earlier notation. So this is given here as 1A, 2A, 3A, 4A, 5A, 6A, 7A. Now these notations are important because in some of the books you will see that these notations are used, and in case of your group analysis also you will see these notations are used constantly. So I would suggest that you should remember the previous notations as well as the current notations. What can you classify from here? You can classify your S block, P block and D block from here. If you consider the S block, here you can see that there are two such groups which are under this S block, which is group number 1 and group number 2. Whereas in the P block, we have group number 13 to group number 18. Together, this S and P block elements are named as representative elements. Apart from this, we have a D block and F block. What about D block? So D block is present in between the S and P block, whereas F block is placed in the bottom of the periodic table. Okay, so these are some names which are given here: cerium and thorium, proactinium, uranium. So all of them falls in your F block element. It is very important to learn the name of these F block elements, especially if I talk about the first row. Okay. Now, here are some important points that you should remember. First, what did I say? That groups belonging to S block are 1 and 2. Groups belonging to P block are 13 to 18. For D block, it is 3 to 12. And for F block, it is, again, if you look upon here, then every F block element belongs to the same group. And what is that group? That group is 3. Right? After 57, you can look here, the the atomic number goes to 72. Means 58 to 71 all lies in this same group, which is group number 3. And this is very important to note. Remember that all F block elements lie in this same group 3. Got it? Now we have some other names also for different groups. For example, this is group 18 and all of them are known as noble gases because they are very less reactive due to their complete octet. What is complete octet? 8 electrons in the valence shell. Then this group 17, these are known as halogens, okay, which includes fluorine, chlorine, bromine, iodine, and your enstantine and then septium. Similarly, this group 16 is chalcogen. I would suggest you that you should at least try to learn this periodic table up to period number 5 and your 2F blocks. Okay, try to learn it up till period number 5 and this F block also. Now there are very mnemonics used for this learning thing. We have different for different person. If you want, you can try it by yourself also. For example, this thing if I tell you, so this is T zara half, means titanium, zirconium, hafnium. Similarly, this is Vo Nawab Tha, which is vanadium, niobium, and tantalum. Then we have Karol Motiwala, which is chromium, molybdenum, tungsten. Then Mantakre, which is manganese, technetium, rhenium. Further, we have ferrous, which stands for iron, ruthenium, and osmium. Okay. Then this one is written as Kauwaroi Insan Ase, which is cobalt, rhodium, iridium. Then we have NiPdPt. Now it is very simple, you can just remember it. Then similarly, we can have various mnemonics for it, and it depends upon you which mnemonics you use. But the important part is how to learn this. You must learn this group wise also and in the linear form also. Which by this I mean that if I tell you that what are the elements present in group number 1, you should quickly tell me that those elements are hydrogen, lithium, sodium, potassium, rubidium, cesium. Okay, up till rubidium at least you should remember. Similarly, for group number 2, which are alkaline earth metals, you must remember it as beryllium, magnesium, calcium, strontium. Okay, so this is my point. Of course, you should learn it linearly from atomic number 1 to at least atomic number 54. But the most important part is that you should remember it in the group wise fashion also, because you will see that in a similar group, properties are resembled between the elements. Like this sodium, potassium, rubidium all have the same number of electron in their valence shell. As a result of this, they will show same physical and chemical properties. Therefore, I would suggest you that you should remember this as group wise. You can take more examples. Here you can see that all of these are noble in nature. They do not react with other elements. And why is it so? Why is this resemblance in the properties? Because they are all are falling in the same group. Similarly, if I talk about the most electronegative elements of particular periods, suppose of group 2 or group 3, your corresponding names are fluorine, chlorine, bromine, and iodine, which are again falling in the same group, which is a halogen group. Is it clear to you? So this thing is very important. Now, moving on to the next, I hope this is clear to you. One more important point. If you start from the left hand side and move on to the right hand side, you can clearly see that we are moving from metals onto the non-metals. In between, there is a ladder-like structure: boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and stantine. So this one is forming your metallide staircase. Okay. So this is also very, very important. Their properties are, of course, it is between the metals and the non-metals. Got it? Any doubt in this part? I hope this part is clear to you. And I would request you to please at least learn the periodic table from group 1 to atomic number 1 to atomic number 54, as well as the F block element. I will try to give you the mnemonics to learn this F block element in the D and F block chapter. Got it? And second thing, how you should learn it? You should learn in the group wise fashion also, because in the group the periodic properties are same. Chemical properties and physical properties both remain same in the same group. Now one more important thing, what you can derive from the group number and period number. So if I talk about the period number, suppose if I take the example of lithium, so it falls in the second period, right? This one falls in the second period and the first group. Very clear, it's very simple and depictable. Now if I talk about the group number, it tells us the valence count of the electron in most of the cases. Now there are anomaly for the D block elements, but for the S and P block element, your group number will tell us the number of valence electron. So for all the elements, helium, lithium, sodium, potassium, rubidium, cesium, francesium, all have one valence electron in their outermost shell. Similarly, for beryllium, magnesium, calcium, strontium, barium, and radium, all have 2 electrons in their valence shell. But what about the period number? What does it tell us? It tells us about the maximum principal quantum number possible in its electronic configuration. For example, if I take the example of lithium, its electronic configuration would be 1s2, 2s1, right? 3 electrons. Now the maximum principal quantum number value is 2 here, and that is the reason it is falling in the group period number 2. You can also take the example of your potassium. You will see that the valence electron is falling in the 4s1, and the maximum value of principal quantum number possible in its electronic configuration is 4. So these are the two things you can derive from the group number and the period number. Got it? I hope this part is clear to you. So we shall now move forward. Okay, some more points regarding the F block element. We will try to discuss it in detail in that chapter also. Electronic configuration is something which is also very important, and it is kind of similar or follow a particular trend, but you will see anomaly in the periodic table regarding the electronic configuration, especially in the D block element and the F block element. So let me make a very important point here. The important point is that your S block element and your P block element, they have no anomaly in the electronic configuration. Take any element if you want. You will see that there is no anomaly at all, especially for S and P block in the upper region. But as soon as you move to this D block and F block, you will see that electrons are making mischievous mistakes in their normal categorization, and they show deviation from the expected electronic configuration, and that result straightforward comes from the half filled and full filled and shielding effect of the electrons. So we will talk about this anomaly in the D and F block element because it is most often seen in the D and F block elements. Got it? I hope so far I am clear to all of you. Now, moving on to the classification of elements. First of all, depending upon the orbital in which the last electron enters, your elements can be divided into first one group 1 and group 2. As I said, group 1 are alkali metals and group 2 are alkaline earth metals. And their last electron belongs to the s orbital, and that is the reason we call them as s block elements. What is the general electronic configuration for it? It is ns1 to 2. Okay. So the previous configurations are known to you. They will not vary at all. But the outermost configuration will be ns1 and ns2. So for group 1 it will be ns1, and for group 2 it will be ns2. Moving on to the group 13 to group 18, if you consider, which is your p block elements, excluding your helium. So helium is an exception here, remember, because helium has only configuration of 1s2. There is only one shell possible in it. Therefore, it will not show the similar electronic configuration, general electronic configuration, as that compared to other p block elements. But still it belongs to the p block. Now, what is the general electronic configuration? It is ns2np126. Means the s orbital will s subshell will always have 2 electrons, whereas p can have electrons from 1 to 6. For example, if you take the example of nitrogen, the electron count which is present there is ns2np5. Then if you move on to your, suppose, oxygen, it is ns2np4, sorry, np6, right? So in this way it will keep on increasing. Okay, let me just tell it once more. For nitrogen it will be ns2np3, and for oxygen it will be ns2np4. Got it? For your upcoming, which is fluorine, it is ns2np5, and similarly for the upcoming noble gas it is ns2np6. So basically here ns2 is remaining constant for every p block element. The number of electron is changing in case of the p subshell. So together we call this s and p block elements as representative elements and the main group element, and therefore the chapter which you will see in the upcoming classes, which is the main group elements, is coming from this naming. Okay, so together this alkali metal, alkaline earth metal, including this group 13 to group 18, are known as representative elements or main group elements. Moving on to the anomalous behavior. So this is something which is important because mostly you will see questions from exceptions, and exceptions come from this anomalous behavior, which is a result of diagonal relationship. Now we'll try to discuss this in detail. So it is seen that for members of each group of S and P block, remember, not the D block, only the S and P block, the first member shows different characteristics from rest of the elements that are present in the same group. Okay, for example, if you start hydrogen, helium, lithium, beryllium. So this beryllium, which is the first member of the group 2, it shows different properties apart from the other parts of the group, which includes magnesium and all. Got it? Similarly, you will see it for the lithium as well. Now, why it is happening? It is due to its small size. So the very first element of every group of S and P block are having very small size. And due to this small size, they have a high electronegativity and high charge density due to the small size, because the charge is same and the size is small. So that creates a high charge density. As a result of this, compared to other elements of that same group, it will show different property. And this element will show a similar behavior to a diagonal element, and that thing is known as diagonal relationship. Now let me just give you a illustration here. So we are taking the second period. Remember, we will take the second period and not the first period. Every element of the second period, starting from lithium. Okay, so first one in the first group we have lithium. So lithium will show properties which are similar to that of magnesium and not sodium. Similarly, beryllium will show similarity in properties with respect to the aluminium. Boron will show similarity in properties with respect to the silicon. Okay, so you can clearly see that there is a diagonal relationship between the elements. And why it is happening? Two reasons are there: small size and high charge density. Okay. Next, if I talk about the remaining groups, which is group 3 to 12, it belongs to the D block elements because their last electron enters a D subshell. And if I talk about the two outermost shell of the D block elements, they are always incomplete. What is the electronic configuration? It is n-1, D1 to 10, ns0 to 2. So in some cases, you will also see that there is ns0, means there are no electrons in the s orbital, but there are electrons in the d orbital. Can you give me the example of such a D block element which has an electronic configuration of ns0 and nd n-1 d10? Anyone? Can you give me an example which is having an electronic configuration of ns0 and n-1 d10? So It is an anomaly in the electronic configuration. Please just write it down here if you know it, or else I will tell you. If you don't know, no issues. Can you tell me which element shows an electronic configuration of ns0 and n-1 d10? I will wait for one more minute. Anyone who knows what is the electronic configuration, which is the element which shows an electronic configuration of ns0 n-1 d10? Okay, so that element is palladium. Now, this is an anomaly in the electronic configuration. It has an electronic configuration of 4d10 5s0. Now, if I consider the n plus n rule here, according to that rule, your 5s is something which is having a lower n plus l value, but still there are no electrons present in it. Instead of that, electrons go directly to a higher orbital or higher subshell, which is n4d, and the reason is the presence of complete d subshell. So when you put 10 electrons in this d subshell, you will see that the ns0 is not filled at all. Now moving on to the next, we have f block elements. The general electronic configuration of f block element is n-2 f1 to 14, then n-1 d0 to 1 and ns2. Now this part is very important here. Means d can have only two possible electron count, which is 0 and 1, and your f will have electron from 1 to 14, whereas there will be two electrons in the s subshell. Got it? Here, of course, since it is a f block element, though the last electron will enter the f orbital or the f subshell, there are two series possible in it. One is 4f and the other is 5f. So in the 4f, we call it as lengthenoid. So here the last electron enters the 4f subshell, and in the case of actinoids, the last electron enters the 5f subshell. Can you tell me what will be the general configuration of lengthenoid specifically? So just put the value of n as 4 here. Then according to that, here we will get, take the value of n-2 as 4 here. So here you will get 6f, then here you will get as 3d, 5d, and here you will get as 4s. Okay, so that would be the general electronic configuration if you take the value of n-2 as 4. Similarly, if you take the value of n-2 as 5, then here it will be 7f, here it will be 6d, and here it will be 5s. Got it? This elements, which is your f block element, they are also known as rare earth elements. Now, why are they called as rare earth element? Because their finding is very less in the global sense. Okay, so the percentage of this element present in our Earth's crust is very less, and the major part of scene is seen in the China. Okay, this rare earth element, for which it is having very benefits also, because this rare earth elements has a large application in the current scenario of the science. Okay, now moving on to the next important thing, which is nomenclature of elements whose atomic number is greater than 100. So we have a general rule for naming the compounds whose atomic number is greater than 100, and this was put forth because there was a confusion for some elements because they were being discovered at the same time in two different places. To avoid the conflict between that two places or between that two countries, we took a neutral path unless its discoverer was not confirmed, and that neutral path was taking a nomenclature fashion of naming the elements, and it was specially done for the elements whose atomic number was greater than 100. Can we take example? Yes, we can have 101, 102, 103. So all of them can be named using this new IUPAC system. What we do in this, suppose your digit which is given is 101. Okay. So for 1, what is the name or what is the root? It is un. Then we have 0. For 0 it is nil. And again for 1 it is un. So you will write it in same fashion, un, nil, un, and lastly you will put em at the last. So un, nil, nil, unnium. Got it? Similarly, if it is 112, it would be unbium. As simple as that. You have to simply put the root and IUM at the last. Then what will be the symbol? So there must be a symbol for that element also. So that would come from the abbreviation. Suppose your element that you have found is 102. Then what would be its name? Its name would be unnibium. And what would be its abbreviation? It will be U and B. Okay, in the same fashion, you will only take this U in the capital letters. Because for every element, if you see, the atomic symbol is having the first letter in capital. Okay, in caps. You can take for calcium or for example for krypton, you will see K is written in the capital sense. Similarly, if I taking the element as 10T, then you will write it as capital U, small n, small b for the symbol of that particular element. So, can we take examples of it? So, we are taking this 101 number element. How you will name it? So, for 1, you will use un. For 0, you will use nil. And for 1, again, you will use un. So, its name would be un, nil, unnium. Okay. Then, what would be its symbol? So, for un, we will take the u. For nil, we will take the n. And for again, un, we will take the u. So, it will be UUN with the first UNU with the first letter which is U as capital. Okay. Now moving on to the periodic trends. So first of all, we will start with the atomic radius. Before moving on to atomic radius trend, we should see that what is atomic radius. I guess it is quite simple to see, but it has various sense in different cases. So if I just try to arrange the periodic table in the increasing order of atomic number, then you will see that in the same order, your atomic radius is decreasing across a period, and if you go down the group, the radius is increasing. Got it? And you will see it for various properties, means there is a variation for various properties. So all of these properties are mainly related to the atomic radius. So first you should know what is atomic radius. It is basically the distance from the center of the nucleus to the outermost shell, which contains the valence electron. Now, as I said, it can be inferred in different sense. It can be in the covalent sense or metallic sense also, depending upon the compound which you are dealing with. If it is a non-metal, you will take the covalent molecule where the two atoms will be of the same type. Okay, and then you will try to calculate the covalent radius with the help of the distance between the two nuclei taken as half of the initial value. Similarly, the metallic radius is considered for metals, and for that we take the crystal lattice of that particular metal. As I said earlier, so if you move across a period, your atomic radii will decrease, and if you move down the group, your atomic radii will increase. The reason is that when you are moving across a period, the effective nuclear charge is increasing because the number of electrons in the outermost shell is increasing. As a result of that, you will see that your outermost shell will experience a greater electrostatic force of attraction that will shrink your atom to a smaller size as you move across a period. When you move down the group, you are increasing the number of shells, right? And this increased number of shells results in greater repulsion and hence greater size at the same time. So it is very important to understand this trend of atomic radius. As I said, what are the types of atomic radius? So first one is covalent radius. In case of covalent radius, we take it for non-metals. Now, all of the non-metals, you know it very well, they exist in homodiatomic molecule form as well. You can take nitrogen, you can take chlorine, oxygen. So all of them exist in diatomic form, O2, N2, H2. So in that case, how we will calculate the covalent radius? We will simply take the distance between the two nuclei and divide it by 2 to get the covalent radius of that particular non-metal. Now question arises, why are we considering the covalent radius and not directly the atomic radius of a isolated atom rather than calculating its distance in a combined form? The reason is that because these atoms are too small and highly unstable. Two things are there. They are too small and highly unstable. So it is very difficult to isolate them first of all. If somehow you are isolating it, then due to small size and due to our lack of instrumental application, you cannot determine the size of such small particle. So we take the combined form rather than taking an isolated form. Got it? Now, here DAA is the bond length, which is basically the distance between the two covalently bonded atoms. What is the next type? It is for heterodiatomic molecule. Now this is something which can be used if you know the electronegativity as well. Okay, you cannot apply it directly to calculate the atomic radii of A in the combined state of heterodiatomic state. Okay, you can use it for homodiatomic, that formula. If it is heterodiatomic and if you want to calculate the atomic radii from this heterodiatomic molecule, means the two atoms are different, then you need to know the electronegativity. Now here also there is a case, if the difference between electronegativity is very small, then the bond length is simply Ra plus Rb. Okay, there is no variation, it will remain the same. But if it is not small, then we cannot use that formula. So here Ra and Rb are the covalent radius of A and B respectively, and chi A and chi B are the electronegativity. As I said earlier, if it is not small and the amount is the distance difference is significant, in that case you will use the formula for calculating the distance between A and B as Ra plus Rb minus 0.09 chi A minus chi B. Okay, so this would be the relation in case of your considerable electronegativity difference. Okay, I hope this is clear to you. Now moving on to the next type, we have this metallic radius. Very simple. In metallic radius, we calculate the distance between two atoms which are present in a given lattice next to each other. Then to calculate the radius of that particular element, we simply divide that distance by 2. So R dash will is equal to D by 2, where R dash is always greater than the actual size of atom. Okay, and D is the distance between adjacent metal in the metallic lattice. Next type. So next we have van der Waals radius. What does it mean? So it is taken for noble gases. Okay, this is taken specifically for noble gases, but you can calculate it for other elements as well. So basically in noble gases, we know that they are not available in combined state. Apart from other elements like N2, O2, H2, you won't see a helium-2 or you won't see a argon-2. This is not possible because noble gas is highly unreactive due to its complete octet. So for those cases, we consider the van der Waals radius. What is van der Waals radius? Suppose D is divided by 2. Now here D, it is something different from the previous case. It is the distance between the nuclei of two non-bonded isolated atoms. Okay, so there we were taking the two atoms which are bonded to each other. Here we are taking the distance between the two atoms which are non-bonded to each other. And always remember, this covalent radius will be greater because the distance between non-bonded atoms will be greater as compared to the bonded one. Because during bonding, there is a case of overlap and the nucleus come closer to each other. As a result of this, distance decreases. But if it is non-bonded situation, then in that case, they will repel each other due to electronic cloud around them. And as a result of this, the distance will come out to be larger as compared to the normal radius. So remember, this will give you a very, very large size as compared to the actual size, and it is not good to consider van der Waals radius. But in case of your noble gas, it becomes a measure to do the same. Okay, you can't take any other step. It is not possible to calculate its radius in the combined state. Now, if I try to just measure all of them, then the largest one is the van der Waals radius. Then we have metallic radius. And lastly is covalent radius. What is the reason? The reason is overlap. So in case of covalent radius, there is an overlap between the atomic orbitals of the particular atom to form bonds. Okay. As a result of this, the distance between the two nuclei decreases. Suppose these are the two atoms, right? In case of non-bonded situation, they will be apart from each other. But in case of covalent radius, they will overlap with each other to form bonds. As a result of this, distance will decrease and hence it will be the smallest one. Then comes your metallic radius, in this case we have some sort of overlapping. Now in case of van der Waals radius, there is no overlap at all. They are present completely apart from each other, so this distance is largest one. Okay. Now lastly, at the end of the period, you will see that there is the presence of inert gas, and as a result of this, you will see that its radius is always larger than the radius of other elements, because for the noble gas we take its van der Waals radius, and it is the result of this taking of this van der Waals radius, you will always see that its atomic radius is greater than other elements in the same period. So this is seen generally in all the cases. Moving on to the next. Lastly, we have this ionic radius. So it's very clear from this term as well that this is considered for the species which are present in charged form or ionic form. Okay. Now there is a very important rule here. If you consider the size of cation, then the size of cation is always smaller than the neutral atom. Why is it? Because the number of electrons are less as compared to the neutral atom. As a result of this, you will see that your electrons will experience a greater effective nuclear charge, because the count of proton is same, but the electron count has gone down. So the same amount of proton will apply a larger force on this electron, and hence your atom will shrink. Got it? So remember that your cationic radius or cationic radii is always smaller than the neutral atom's radius. Whereas if you consider the anionic radii, then in that case its size is always greater than the neutral state, because in the case of anionic region, you will see that an extra electron is being added to that atom. Okay. Now, due to that extra electron, there will be repulsion, and that repulsion will allow the atom to expand, and hence the size of an ion is always greater than the neutral atom. So two things you must remember, this is very important, that cationic radii is always smaller than its neutral atom. For example, Na will have a bigger radius as compared to the Na plus, whereas in case of anion, Cl minus Na plus will have a smaller radius as compared to the Na, whereas in case of chlorine, the Cl minus will have a greater radii as compared to the Cl. Okay. Now, next, this statement that you are seeing, it is mostly true for isoelectronic species, means those species which have the same electron count. It is seen that for isoelectronic species, with increase in negative charge, the ionic size increases, whereas with decrease in positive charge, the ionic size increases. Okay. So basically, if you are increasing more and more negative sign for isoelectronic species, then the one with the greater negative sign will have a larger size, and the one with a greater positive sign will have a smaller size. For example, if you take O2 minus and F minus, they both are having the same electron count. Okay, just count it, it's very simple, but the charge is different. In case of oxygen, there is 2 negative signs, so it will have a larger size. Whereas if you consider this with the sodium plus, which is also an isoelectronic species with this sodium and oxygen, it will have a smaller size due to greater positive charge. So all of those elements which are having the same size, the one with the greater negative sign is larger in size, and one with the greater positive sign is smaller in size. We can take an example also. For example, we take the case of oxygen. So there are 3 species possible for oxygen: O, O minus, and O2 minus. As I said earlier, the one with a greater negative sign will have a greater size. So O2 minus will have the largest size, then your O minus, and then your O. So this is for your second statement, which says that anionic radii is always greater than its neutral atom, and you can see it clearly. Now, for isoelectronic species, always remember that ionic radii is inversely proportional to magnitude of nuclear charge. Okay, we have talked a lot about this. So this was all for the theory part. Now we will move on to questions. So just wait for a while. Let me move on. Let me turn on the questions. Meanwhile, if you have a doubt, you can just post it here in the comment section. So here is your first question. You have to say that the periodic number in the long form of the periodic table is equals to. So we have talked a lot about this. You have to tell about the period number. First option is it equals to the magnetic quantum number? Second, equals to the atomic number. Third, equals to the maximum principal quantum number. Or fourth, equals to the maximum azimuthal quantum number. So what will be the answer for this question? What will be the period number equals to in case of long form of the periodic table? So I will give you some time to think about it. It's a direct theoretical question. You can just post your answer in the comment section. Okay, option number C. Anyone else? Okay. So let's see what is the correct answer. It is obviously option number C. So each period begins with the distribution of electron in a new principal quantum number. You can take any example. It starts with the S subshell of that particular quantum number. And that is the reason it is having the value of maximum principal quantum number. So we can say it that period number is equals to the maximum n of any element, where n is the principal quantum number. Now this statement is quite simple, but it's very important at the same time. Why I am telling it? Because in many situations you will see that you don't know the principal quantum number, but you are knowing the period number. Got it? So in that case you can directly use it, or you can use it to get the electronic configuration. Okay, moving on to the next question. We have to tell that which pair of atomic number of elements has same chemical properties. So how can we know the chemical properties? It directly comes from the period number. If the period number is same, then those two elements will have the same chemical properties. And when is the period number same? It is same when the valence shell count is same. So just try to get the electronic configuration for each of this case and see that which of them has the same count of valence electron. So that would be your answer. So it's a easy one. Again, anyone who can just solve it, post it in the comment section. So it's a very simple one. Starting from 1322, you can use the simple electronic configuration also. For here, B option, it will be 2 1. This will be 2 8 1. This is 2 1. This is 2 8 8 2 1. Okay. Just see that which one is having the same valence count. Okay. So I hope you must have find it out. Similarly, for option number D, it is 2, and for 4, it is 2, 2. Anyone? What is the correct answer? Option number B. Anyone else who got the answer for this question? Which of the following pairs of atomic number will have the same chemical properties? Just count the valence shell and see that whether they are falling in the same period or not. So moving on to the correct answer, it will be option number B. Very good. If I talk about option number B, the electronic configuration for 3 and 11 would be, for 3 it will be 1s2 and 2s1, and for 11 would be 1s2, 2s2, 2p6 and 3s1. Now both of them are belonging to group number 1, and this is simply hydrogen, helium, lithium. So this is your lithium and this is your sodium. Okay, and since both of them are falling in the same group, therefore they will have similar chemical properties. Next, question number 3. Both lithium and magnesium display several similar properties due to diagonal relationship. However, the one which is incorrect is, so the physical and chemical properties are quite similar, but there is a difference between diagonal elements as well. You have to see that which of these 4 is not true according to that. First one is both form basic carbonates. Second is both can form soluble bicarbonates, means they are soluble in water. Third one is they can form nitrites. And fourth one is that nitrates of your lithium and magnesium are yielding NO2 and O2 upon heating in the presence of oxygen. So it's a very simple one, just try it by yourself. This is direct theoretical question. So I would advise you, so from this question you can get a simple advice that try to see that what are the similar physical and chemical properties in case of elements if they are present in a diagonal relationship. Also see the point of difference between both of them. Okay, so questions are asked from here, from this diagonal relationship part. And what is the reason? That is the most important part. It is the charge which is present in a small area. As a result of this, there is a high charge density in that atom, and hence both of them show the similar properties. Anyone who got the answer? Okay, so the correct answer will be both of them form basic carbonates. So basically, magnesium is something which is capable of forming basic carbonates because lithium cannot form normal carbonates. Okay, why is it so? What is the reason behind it? That the reason is that your lithium is only forming the normal carbonate. Sorry, it can form the normal carbonate because it has no extended valency, right? As compared to magnesium, which has available S and Pa as well, it has no available Sp and D. As a result of this, it can only form normal carbonates like Li2CO3. Whereas magnesium, if it is reacted with carbonates, then it can give a basic carbonate. See, MgOH whole twice. So this is representing a basic part of this given carbonate. Next, so this is a direct theoretical question. If you are not able to solve it, don't worry. Okay, these questions are something which is quite belonging to luck. Okay, if you know the theory directly, you can solve it. If you don't know, you can't solve it. But try to solve the logical questions like this one. So it tells us that you have to decide that which of this is given atomic radii of fluorine and neon. Now you can see that there are 4 options, and you would ask that how it is a logical one. It is a direct theoretical question. But remember, we talked about this van der Waals radius and covalent radius and all. There we have talked about a specific property of van der Waals radii, which is having a large size. So from that perspective, you can easily give your answer. If anyone who is getting the answer, you can just post it in their comment section. So 4 options are given here, 0.7 to 1.60 respectively for fluorine neon. Then we have 1.60 for both of them, and we have 0.72 for both of them. Last one is none of the above. So what will be the correct answer? Remember, your noble gas have greater radii. Okay, option number A. Let's see if it is correct or not. So, yes, the correct option is option number A. What is the reason behind it? Basically, in case of neon, which is a noble gas, we take the van der Waals radius. And van der Waals radius is taken for those atoms which are not bonded to each other, means they are present in non-bonded situation. Okay. Now, since they are not bonded to each other, therefore there will be no overlap between them, and hence they are present at a distance apart from each other, and that creates a greater magnitude of the van der Waals radius. So here you can clearly see it is 1.60. But actually, if you move from fluorine to neon, it is not the case. Got it? Next one. You have to decide that which one has the highest value of ionic radius. Okay, 4 options are given here: lithium 3 plus, beryllium 3 plus, F minus, and O2 minus. Now, two things are to be applied here. Means two trends are to be applied here. First one is that if you move down the group, the size increases. Second thing, if you are increasing the negative charge for isoelectronic species, then in that case, the size will increase with increasing negative charge. Anyone who got the answer? It's very simple. So two things are to be applied here. First of all, the ionic size increases as we move down the group. And second thing, for isoelectronic species, the size increases with increasing negative charge. What will be the answer for this question? Yes, you are absolutely correct. Hope you will do the same in the JEE exams. If you find an option to take it as E. Okay. Yes, the correct option will be option number D. So, why is it so? It's very simple. If you consider other parts of the option, then there we have B3 plus and we have a much smaller Li plus, which belong to the period number 2. Whereas these two, oxygen and fluorine, are coming in the latter part. Got it? But if you compare oxygen and fluorine, oxygen has a greater negative charge. As a result of this, due to higher negative charge, it will have a higher repulsion and hence it will have a greater ionic radius as compared to F minus. Okay. Next question. You have to decide that which of the following series of elements have nearly the same atomic radii. Again, this is a question which can be difficult for you because for so far you have not dealt about this DNA block. But still, if you know, you can answer it. For fluorine, chlorine, and bromine and iodine, option A. Then we have in option B, we have sodium, potassium, rubidium, and cesium. Option C, we have lithium, beryllium, boron, and carbon. And option D, we have iron, cobalt, nickel, and copper. How can we solve it? So, to think about it, we should know that if I try to solve it in a logical way, suppose. So, these elements that you are seeing, these groups of elements that you are seeing, in all of these elements, the group number is different. Sorry, the period number is different. We are going down a group. Fluorine to chlorine, chlorine, bromine, then iodine. Similarly, sodium, potassium, rubidium, cesium. Then here also lithium, beryllium, boron, and carbon. Okay, so we are changing the period number. When we are changing the period number, there is a very vast difference in the atomic radii. What is the reason? The reason is that because these elements are seeing a change in the number of shell. Okay, the number of shell is changing here. For fluorine and chlorine, there is increased by a shell of increased by a number of one shell. Similarly, in bromine, there is again an increase of one number shell. In iodine, there is again an increase of shell. You can say the same for the option B and C also. Although boron and beryllium are belonging to the same period, but lithium and beryllium, that is something which is belonging to a different one. Okay. Now, if I consider the D block, which is this one. Okay, so this one is belonging to the same period. Lithium, beryllium, boron and carbon, they are belonging to the same period. Sorry. But if you consider these two options, option number C and D, then the C group elements, the C option is collecting those elements which are present in the second period, right? They all are present in the second period. And in case of second period, there is no involvement of D subshell. Okay. Where in case of the D option, all the elements are coming from the D subshell. In case of D subshell, there is a very important point, which is the diffusion part. Okay. So the D subshell is very much diffused. As a result of this, the effect of nuclear charge is not that much dominant. And hence, on moving across a period, the change in effective nuclear charge has no dominating effect on its size. So, as a result of this, the size is not changing that much variantly as compared to the lithium, beryllium, boron and carbon. Hence, the correct option will be option number D. So, if I try to tell it in a direct sense, then my answer would be they all are belonging to transition elements, and transition elements have electrons present in the D subshell. Okay. And in case of D subshell, the size is very much diffused, and as a result of this diffused or flattened size, it will have a very less effect of increasing effective nuclear charge, and hence its size will not vary drastically for the iron, cobalt, nickel and copper. Okay. You can look upon the graph as well. The graph almost goes linear or parallel to the x-axis if x is taken as the atomic number. Next, easy one. So here we have chloride ion, potassium ion. So they both are isoelectronic, means they have the same count of the electron. You have to see that what is the comparison between their size. So what is the relation between your size and charge? In case of isoelectronic species, it's very simple. Greater is your negative charge, larger is your size, and greater is your positive charge, smaller is your size. And your neutral parts belong to the intermediate one. Okay. So it's very clear that out of these two options, which will be the correct? Which one will have a larger size, chloride or potassium? Anyone? Option number B. Okay. Yes, the correct option will be option number B. So if I compare chlorine and potassium, it is very clear that chlorine is having a negative charge and potassium is having a positive charge. Since chlorine is acting as an anion here and potassium is acting as a cation here, and due to their isoelectronic nature, the size of chlorine will be greater. Why? Because due to greater repulsion, the atom will spread out to decrease this increased negative charge or to decrease this increased repulsive forces. Then our next question, here we have 5 elements in total. Okay, they are present in their ionic form, O2 minus, F minus, sodium plus, magnesium 2 plus and aluminium 3 plus. It is already given in the question that all of them are isoelectronic in nature. You have to tell that what is the order of their ionic radii. Okay. First option is an increase from O2 minus to F minus and then decrease from Na plus to Al3 plus. Second one is a decrease from O2 minus to F minus and then increase from Na plus to Al3 plus. Option number C, a significant increase from O2 minus to Al3 plus and a significant decrease from O2 minus to Al3 plus. So the order is already given. You have to put just your greater than sign or less than sign. How you will solve it? Again, you will use that same logic of your charge and size relation, since they are the isoelectronic species. So we have a answer here, option number D. Okay. So let's see what is correct. The correct answer would be option number D. Very good. So if I consider isoelectronic species, so this all ionic radii is inversely proportional to the negative charge, right? So what are the species that are given here? We have O2 minus, F minus, Na plus, Mg2 plus and Al3 plus. Their atomic number is given below. Why are they isoelectronic? It's very simple. So if there is a negative sign, just add that amount of sign to the electron count. So here the electron count would be 10. For F minus, again it will be 10. For positive sign, again you will decrease the number of your electron. So it would be 10 here. For magnesium 2 plus, again you will decrease the electron count by 2 to calculate it from the atomic number. So 12 minus 2 it will be 10, and from 13 minus 3 it will be again 10. So all of them are having the same electron count. Now if that is true, then the greatest charge, negative charge, is present in oxygen. So it will have the largest size. Then comes your F minus, then comes your sodium plus. After that we have magnesium 2 plus, and lastly we have Al3 plus. So this is your overall answer. Anyone who has a doubt in this? Is it clear to all of you? Is it clear to all of you? Is there a doubt? So I will now ask you a question from anomaly part. Okay. So if you know the answer, just quickly tell me. So I will give you two options for every question, and it would be kind of rapid fire, right? Okay, so this will be directly from the anomaly part. So be ready. So I have few questions. I will dictate you and give you only two options. Can I start? Can I start my quiz? Because this chapter mainly asks questions from the anomaly. Okay. If you have a doubt in this part, then you can ask me. Okay. So the first question is that, can you tell me uh, can you tell me that what is the electronic configuration of chromium? Just write it quickly here. What is the electronic configuration of chromium? Anyone? What is the electronic configuration of chromium? So I will wait for one more minute. Okay, so it would be 4s1 3d5. Yes, because it has a eager to have a half filled d orbital. Okay, so that is the reason it is having a electronic configuration of 4s1 3d5. So just write it for the outermost configuration. Okay, similarly, can you tell me what is the electronic configuration for palladium, the outermost one? Tell it for 0 for s and d only. Anyone who got the answer? So what would be the electronic configuration of palladium? So I'm seeing the answer 4s2 3d3. Okay, anyone else? So these are questions that are directly asked in your JEE exams, which includes the anomaly part, right? So that electronic configuration is 4s0 5d10. So a last question for you, since we are lacking time. Why NCl5 is not possible while your PCl5 is possible? Okay, so you know the compound PCl5, but we don't have a compound such as NCl5. Do you know what is the answer for it? So why is NCl5 not possible whereas PCl5 is possible? Anyone who has the answer for this question? Okay, so the reason is that due to unavailability of d orbital in case of nitrogen. Okay, so due to that reason, your NCl5 is not possible. So this was all for today's class. Thank you for joining the session. I hope you enjoyed it. Okay, so if you have a doubt, you can just come to our doubt clearing session, which starts from 10 a.m. in the morning to 6 p.m. in the evening, or you can drop your specific questions also in the SATHEE forum. Okay, well tried. NS are only 3 electrons for sharing. Yes, the appropriate reason would be the unavailability of d orbital. Okay, so and nitrogen has a very small size, and to put all the chlorine around it, it would be a congested situation. Okay, and you would also not see nitrogen to have such higher uh, accommodation of elements around it. Got it? Okay, thank you.
Hello everyone. So in today's lecture, we will discuss definite integral. Okay. This is disclaimer. So first here, we will discuss the concept of definite integral. What is the meaning of definite integral and how it is different from indefinite integral. Okay. Then we will evaluate definite integral using substitution. Okay. How we can find a definite integral using the substitution method and how this substitution method is differ from the substitution method of indefinite integral. Then today we will tell you about the properties of definite integration. What is Leibniz theorem and how Leibniz theorem is helpful to calculate definite integral. Okay. Wallis formula. After that, we discuss inequality in definite integral and definite integration as the limit of sum. How we can represent our definite integral and integration as a sum, as a limit of sum. Okay. And then we will discuss some particular cases. Okay. So let's start. So what is definite integral? So if we have a function fx, then what is antiderivative for this function fx? The function phi x is antiderivative for a function fx defined on interval a to b. If we differentiate phi x, we get fx. Okay, that means phi dash is equal to fx, then phi x is antiderivative of function fx. Clear? Then definite integral of fx over this interval, closed interval a to b, is noted by integral a to b fx dx. Okay, here a is lower limit, b is upper limit. So now we find the value of integral of function fx from this lower limit value a to upper limit b, and that is defined as, that means it is equal to phi b minus phi a, where phi x is antiderivative. So the value of definite integral is equal to phi b minus phi a, where phi b is the value of antiderivative at its upper limit minus value of function antiderivative at lower limit. Okay, that is definite integral of function fx from lower limit a to upper limit b is equal to phi b minus phi a. Okay, here a and b call the limit of integration. A is your lower limit and b is your upper limit. Okay, so to calculate definite integral, that is noted by integration a to b fx dx, we have to calculate the antiderivative of function fx, and when we have the antiderivative of function fx, that is noted by phi x, we just calculate difference of the value of function phi x at upper limit minus at lower limit. Okay, and that is the value of this definite integral. So the value of definite integral must be a constant, a real number, but when we calculate the indefinite integral, we get a function. That is the basic difference between indefinite integral and definite integral. Okay, so some note. First, every definite integral has a unique value. Okay, so if we have a definite integral, then its value will always be unique. Second, the above definition, what we read about definite integral, is nothing but the statement of second fundamental theorem of integral calculus. So second fundamental theorem of integral calculus gives the method to calculate definite integral. Okay. Now, what we mean about definite integral? What is a geometrical interpretation of definite integral? So, when we calculate this definite integral for a function fx from the lower limit a to upper limit b, so fx is a function, so it must be a curve. So this definite integral value gives the area of the region bounded by the curve, the x-axis and the ordinate x equal to a and x is equal to b as shown in this figure. So y is equal to fx is our curve. So when we calculate the definite integral for this function fx from lower limit a to upper limit b, then it means it is the area of this shaded region. And what is this region? This region bounded by the curve y is equal to fx, the line x is equal to a, the line x is equal to b and the x-axis. So this area is given by this definite integral. Okay. So this is your geometrical interpretation of definite integral. Okay. So by using definite integral, now we can find area under curves. Okay. So if we have any irregular curve like y equal to fx, then we can calculate the area under the curve by using the integration. So when we evaluate definite integral using substitution method, so when the variable in definite integral changed due to substitution, then important thing is the limit of integral will also be changed according to the substitution. That means, for example, we will evaluate the definite integral of the form integral a to b f gx into g dash x dx. Okay, we want to find the value of this definite integral, and here we use substitution method. So first step is find the antiderivative for this integral. Okay, that is similar way that how we calculate the indefinite integral. And when you calculate the value of antiderivative, then apply the second fundamental theorem of integral calculus. Find the difference of the antiderivative function at upper limit minus at lower limit. Okay. So how we calculate this? We use the substitution method. We take gx as a new variable t. Okay. Then we differentiate it with respect to x. We get g dash x dx is equal to dt. Then in a second step, we also need to find the new limits for this integral, because when we take the new variable, we also have to find the new limit according to this new variable. So find the limit of integration in new system of variable. Here now the lower limit is GA, as we take gx is equal to t. So at first the limit is a to b, but now the limit is from GA to GB. So my integral is now become integration of ft dt, where t is gx from GA to GB. Okay. And then we evaluate the integral to find the value of definite integral. Okay. Clear? So whenever you use substitution method to solve a definite integral, you must change the limit according to the new variable. Okay. Now we discuss some properties of definite integral. So first one is, when we integrate a function fx dx, from alpha to alpha, that is definite integral alpha to alpha fx dx. So its value is equal to 0. Okay. So the first property is that if you have a definite integral and both lower and upper limit is same, then the value of definite integral is equal to 0. We can relate this with area because definite integral is nothing but area under the curve y is equal to fx and the ordinate x is equal to lower limit and x equal to upper limit, but at lower and upper limit same. So from x is equal to alpha to x equal to alpha, and that area clearly it is 0. So whenever we calculate definite integral from alpha to alpha, that means lower and upper limit is same, then the value of definite integral is 0. Second property, that is definite integral alpha to beta fx dx is equal to definite integral alpha to beta ft dt. Okay, so it means if we change the variable, your definite integral remain the same, it make no difference. Okay, now third property, the definite integral from alpha to beta fx dx is equal to minus integral beta to alpha fx dx. Okay, so if we switch the limit, position of limit, if we take the lower limit as upper limit and upper limit as lower limit, then we just need to take minus in front of integral. So minus of beta to alpha integral of beta to alpha fx dx is equal to alpha to beta integral fx dx. Next property. So next property, that is alpha to beta integral alpha to beta fx dx is equal to alpha to c1 fx dx plus c1 to c2 fx dx plus dot 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 plus integral cn to beta fx dx, where this c1 c2 cn all lies from between alpha and beta. So if we have an interval and we have to find the definite integral on that interval, like we have an interval alpha to beta and we need to calculate the different integral of fx on that interval, so we can split this interval in subintervals. So how we can split? We just take a points between the interval. So just we take alpha to c1, then c2, then cn. So now we can find the value of definite integral in each interval, in each subinterval, and when we sum all the value of definite integral on the subinterval, we get the definite integral of fx on the entire interval. So alpha to c1, then c1 to c2. The points must be continuous. That is, alpha is lower limit, then c1 is upper limit for fx, and then c1 become lower limit and c2 is upper limit fx dx, plus c2 become lower limit and then c3 fx dx in such a way, plus cn to beta fx dx. Okay, this is a very important property. That is, we can break the interval on many subinterval and then find the value of definite integral on each subinterval, and when we take the addition of all the value of definite integral, we get the value of definite integral on entire interval. Okay, property number 5, definite integral from alpha to beta fx dx is equal to definite integral alpha to beta f alpha plus beta minus x dx. Okay, so the value of alpha to beta fx dx is equal to integral alpha to beta f alpha plus beta lower limit plus upper limit minus x dx. These are the property which we use to solve a question. Sometime to find the value of definite integral of alpha to beta fx dx is comparatively difficult, then calculate the value of definite integral from alpha to beta f alpha plus beta minus x dx. Okay. Next, B part of fifth property, that is definite integral from 0 to alpha fx dx is equal to integral 0 to alpha f alpha minus x dx. Here upper limit is alpha and lower limit is 0. The same property as part A, we just take the lower limit as 0. So we get 0 to alpha f alpha minus x dx. Now next property, property number 6, and this property based on even function and odd function. So what is the definition of even and odd function? So if we have a function fx and if f at minus x is equal to f at x, like your function x square, then that function is your even function. And if f at minus x is equal to minus fx, like x cube, then that function is odd function. Okay, so when we find integral from minus alpha to alpha fx dx, then the value depend upon the function is even function or odd function. If the function is even function, that means f minus x is equal to fx, then it is equal to 2 times 0 to alpha fx dx. Carefully observe the limit. First, the limit is from minus alpha to alpha fx dx, but now the limit is from 0 to alpha. So, when the function is even function, that is f minus x is equal to fx, then its formula is 2 times 0 to alpha fx dx. Okay, and when it is odd function, then the value is 0. Okay, so this is your sixth property. Now property number 7, integral 0 to 2 alpha fx dx is equal to, so we can split this definite integral into two parts. First, 0 to alpha fx dx plus 0 to alpha f 2 alpha minus x dx. Observe the limit. In the first, limit goes from 0 to 2 alpha fx dx, and when we split it into two part, now our limit is goes from 0 to alpha, 0 to alpha integral 0 to alpha fx dx plus 0 to alpha integral f 2 alpha minus x dx. Next property, definite integral from 0 to 2 alpha fx dx is equal to 2 times integral 0 to alpha fx dx if f 2 alpha minus x is equal to fx. Okay, and this is 0 if f 2 alpha minus x is equal to minus fx. So we can easily get this formula from above one, that is when f 2 alpha minus x is equal to fx, the value of 0 to 2 alpha integral fx dx is equal to 2 times 0 to alpha fx dx, and when it is equal to minus fx, this is equal to 0. Next property, that is integral alpha to beta fx dx is equal to beta minus alpha. Upper limit is beta, lower limit is alpha. So upper limit minus lower limit into integral 0 to 1 f beta minus alpha x plus alpha dx. So first, in the LHS side, when we calculate this definite integral, the limits are alpha to beta. But when we apply this formula, now we need to calculate the integral from the limit 0 to 1. Very important property. So what is the formula? Beta minus alpha, lower limit minus upper limit, integral 0 to 1 f beta minus alpha, lower limit upper limit minus lower limit into x plus lower limit dx. Okay. Clear? Next point. Now we will discuss about important function, periodic function. Okay, what is the meaning of periodic function? So if we have a function fx, then if we write f x plus t is equal to fx, where t is the period of the function fx, then such type of function is called periodic function. If there is some period, that is value repeated after some value, okay, that is f x plus t is equal to fx, then t is the period of function fx. Okay, so first formula related to periodic function, that is the value of definite integral from alpha to alpha plus n into t fx dx is equal to n into integral 0 to t fx dx, where n is any integer value. So here fx is a function and fx is a special type of function, that is a periodic function, and the period is t. It means fx plus t is again fx. So if we integrate from alpha to alpha plus nt, where n is any integer, then it is equal to n time integral of 0 to t fx dx. Okay, limit is changed. First limit is from alpha to alpha plus nt, but now it is reduced, and now we just need to find the value of definite integral from 0 to t and multiply by n. We get the value of definite integral from alpha to alpha plus nt. Option B, second result, integral from alpha t to beta t fx dx is equal to beta minus alpha 0 to t fx dx, where alpha and beta are any integer. Okay, so to calculate the value of definite integral from limit alpha t to beta t, from lower limit alpha t to upper limit beta t, we calculate definite integral of function fx from 0 to t and multiply it with difference of beta and alpha, that is beta minus alpha, we get the definite integral. C, definite integral from alpha plus nt to beta plus nt of function fx is equal to integral alpha to beta fx dx, where n is any integer. Okay, so third formula is, if your lower limit is alpha plus nt and upper limit is beta plus nt, then this integral alpha plus nt plus beta plus nt fx dx is equal to, just find the definite integral from alpha to beta. Okay, so this is the property related to periodic function. So if your given function is periodic function, then finding its definite integral is much easier. Next property. So let's discuss some important integral that can be derived using the properties that we discussed earlier. Okay, so first, definite integral of function log sin x from lower limit 0 to upper limit pi by 2 is equal to 0 to pi by 2 log cos x dx, and that is also equal to pi by 2 log 1 by 2. Okay, these are some important integral. Second, integration of 0 to pi by 4 log 1 plus 10x dx, and this is equal to pi by 8 log 2. Okay, and this all integral can be obtained, the property what I discussed earlier. Okay, next property, if you have a function fx and that function is not a continuous function, that function is discontinuous, and the points at which they are discontinuous are x1 x2 comma dot 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 xn in interval AB. So these are the point where this function is discontinuous. Then we can define subintervals by using this point of discontinuous. What are the subinterval? A1, A to x1. X1 is the first discontinuous point. Then x1 to x2, comma, dot 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 xn minus 1 to xn. Then xn to b, such that function is continuous in each of these subinterval. Okay. So to calculate the definite integral of function fx dx in a closed interval ab from a to b fx dx, and we know that if your function fx is discontinuous function at certain point between the interval, and that points are x1 x2 comma dot 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 xn, then according to this point we just break the interval into subintervals. If your x1 is your first point of discontinuous, then a1 to x1, then x1 to x2, x2 is a point of discontinuous, then x2 to x3, x3 is the point of discontinuous. In a same way, xn minus 1 to xn and xn to b. Important thing is, in this subinterval your function fx is continuous. So we calculate the value of definite integral on this interval, on this subinterval, and then we take the sum of all the definite interval on the subinterval. We get the definite integral of function fx on the interval ab. So definite integral of function fx to a to b fx dx is equal to definite integral of function fx from a to x1 plus x1 to x2 fx dx plus dot 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 plus xn minus 1 to xn fx dx plus xn definite integral from xn to b fx dx. So this result is very important to find the value of definite integral of function, that which function is not a continuous function, and we know the point of discontinuity for that function. Okay, Leibniz theorem. So what is Leibniz theorem? So if phi x and psi x are two functions that are defined on interval alpha to beta, and also these functions are differentiable function on this interval alpha to beta, okay, and ft is another function, and is this function is continuous on interval phi alpha to phi beta, psi alpha to phi beta, okay. So there are three function, phi x, psi x, ft. Phi x and psi x are defined on alpha to beta, and these functions are also differentiable function on this interval. Ft is another function that is defined on psi alpha to phi beta, and ft is a continuous function. Then Leibniz formula, that is Leibniz theorem, when we differentiate d by dx, so differentiation of this definite integral from phi x to psi x ft dt, okay. So how we find this? So we just differentiate this integral. Phi x is a function of x and psi x is another function of x, that is defined on interval alpha to beta, and these functions are differentiable function. So and ft is another continuous function on interval psi alpha to phi beta. So this is equal to differentiation of psi x with respect to t, with respect to psi x and function value at psi x minus d by dx phi x f at phi x. So by using this formula, we can find the value of differentiation of this definite integral, okay. Okay, now we'll talk about Wallis formula. So this is a special type of integral formula whose limit are from 0 to pi by 2, and the integrand is either power of cos x, power of sin x, or cos x multiplied by sin x. So this Wallis formula is used for a special type of integration. So when we integrate from 0 to pi by 2, for Wallis formula, the limit are from 0 to pi by 2. That means the lower limit is 0 and upper limit is pi by 2. And integrand is of the type like integral power of cos x, integral power of sin x, like cos the power nx, sin the power nx, or integral power of cos x and sin x. So to calculate the definite integral of from 0 to pi by 2 sin nx dx is equal to 0 to pi by 2 cos the power nx dx. This is equal to, so according to Wallis formula, this is the formula. So n is any positive integer. So if n is even, that is n is equal to 2m. So if this is even, then the formula for 0 to pi by 2 sin n the power nx dx also equal to 0 to pi by 2 cos the power nx dx, and that is equal to n minus 1 into n minus 3 into n minus 5 dot 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 5 into 3 into 1 by n into n minus 2 into n minus 4 dot 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 6 into 4 into 2 into pi by 2 if n is even. So if you observe the numerator part, we subtract the odd term. First n minus 1, then n minus 3, then n minus 5, and 5, 3, 1. Okay. And in the denominator, we take the subtract or even term. First n minus 0, then n minus 2, n minus 4 till 6, 4, 2 into pi by 2. Okay. And if it is odd, that is of type 2m plus 1. So if n is odd, then this value is equal to n minus 1, n minus 3, n minus 5 dot 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 6 into 4 into 2 by n into n minus 2, n minus 4 into dot 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 5 into 3 into 1. Okay. Now for cos x into sin x, if we have an integral power of cos x and sin x, like we need to calculate the value of definite integral from 0 to pi by 2 sin the power mx into cos the power n x dx, then this is equal to, when both m and n are even positive integer, then this is equal to m minus 1, m minus 3 dot 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 2 or 1, okay, into n minus 1, n minus 3 dot 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 2 or 1, okay, by m plus n minus 2 dot 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 2 or 1 into pi by 2. And if your m or n, either any of them is odd or both are odd, then the value of definite integral from 0 to pi by 2 sin the power mx into cos the power nx dx is given by m minus 1 into m minus 3 into dot 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 2 or 1 into n minus 1 into n minus 3 dot 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 2 or 1 by m plus n minus 2 into dot 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 2 or 1. So by using this Wallis formula, we can calculate the integral power of cos x, sin x, cos x and sin x between the limit 0 to pi by 2. Okay. Okay. So now we will discuss some inequality based on definite integral. The first one is, if fx is greater than equal to gx on the interval alpha to beta, then the value of definite integral from alpha to beta of function fx dx is also greater than equal to the value of definite integral of gx from alpha to beta. So if fx is greater than equal to gx on that interval, then definite integral of alpha to beta of fx dx is also greater than definite integral alpha to beta of gx dx. Second, if f of x is positive or non-negative function, that is fx is greater than equal to 0 in the interval alpha to beta, then definite integral of this function from alpha to beta is also greater than equal to 0. Okay. Next, if there are three functions fx, gx and hx that is defined on interval a to b, and all three functions are continuous function and such that fx is greater than equal to gx and less than equal to hx, then definite integral of fx from a to b is also greater than equal to definite integral of gx from a to b and less than equal to definite integral of hx from a to b dx. Okay, so this if this inequality follow, then definite integral also follow this inequality. Next, if your function f is continuous on interval alpha to beta, then if fx lies from L to m for all x belongs to alpha to beta, then definite integral of fx from alpha to beta lies between L into beta minus alpha and m into beta minus alpha. So if your function fx is greater than equal to n and less than equal to m for all x belong to this interval, then the value of definite integral of fx from alpha to beta is greater than equal to L time beta minus alpha, L time upper limit minus lower limit, and less than equal to m time upper limit minus lower limit. Okay. Next, if f is continuous on alpha to beta, then important inequality is that mod of alpha to beta fx dx is less than equal to definite integral from alpha to beta mod fx dx. Okay, so if your given function f is continuous and that is defined in the closed interval alpha to beta, so when you calculate this mod value, that is mod of alpha to beta fx dx, then this is less than and equal to alpha to beta mod fx dx. Next point, if your function f of x continuous on interval alpha to beta, then and modulus of f of x is less than equal to k for every x belongs to alpha beta, then the modulus of the integral from alpha to beta fx dx is less than k times beta minus alpha. Okay, so if your function f is continuous and defined on interval alpha to beta, and if the mod of fx is less than equal to k for all k belongs to that on that interval, then the definite integral value, that is mod of alpha to beta fx dx, is less than equal to k time beta minus alpha. Okay. So now we discuss limit of a sum. Okay, how we can write a definite integral as a limit of sum. So suppose we have a function fx and fx is a continuous function and this function defined on a closed interval ab. Okay, then definite integral of function fx dx from a to b is equal to limit n tending to infinity h time summation from r is equal to 0 to n minus 1 into f at a plus rh. So in this case, we represent a definite integral from lower limit a to b fx dx as a limit of sum. Okay, so if we calculate this limit of sum, we get the value of definite integral. So how we do? So we know that definite integral represent the area under the curve, that is the region bounded by the curve, the x is equal to a line, x is equal to b line, and the x axis. Okay, so we also calculate this area as a sum. So what we do, we just split this whole region as a sum of rectangles. Okay, so we split this region as a rectangles. We take a very thin strips, and so if there is a curve y is equal to fx, and then a line x is equal to a and x is equal to b, so that we just split the interval into very thin sub intervals with a width h. So width h is given by b minus a by n, where n is the number of sub interval. Okay, so we get a very thin strip. So when we calculate the area of each strip and take the sum, we get the area of that region, and that is equal to definite integral. That is the whole idea how we can write a definite integral as a limit of sum. Okay, so just take a first strip. So x is equal to a, and then h width, we take then a second first strip. So the width is h for that rectangle, and the length of the rectangle is f at a plus h. So the area of that rectangle is h into f at a plus h. If we take the rth strip, the rth rectangle, so for that the width is same h, but the length of the rectangle is equal to f at a plus rh. Okay, so the area of that rth rectangle is h into f at a plus rh. So when we take the sum of all this rectangle, we get the area of that region. And to get a better approximation, a better approximated value of that area, if we take n tending to infinity, that means we divide this interval tending to infinity. Number of subinterval is now tending to infinity. Then that width of the strip is tending to 0 to get a better approximation. And then that value of sum of all the area of the rectangles is equal to the value of definite integral a to b fx dx. So that's how we can write a definite integral as a limit of sum. Okay, so here h is your width and r represent the number of rectangles. So r is equal to 0 to n minus 1. We just take the n rectangles, and f a plus r is represent the length of each rectangle. Okay, and we find the area and take the sum of all the area. And when we n tending to infinity, that means we increase the number of strip, the width of the rectangle is decreases, is tending to 0, then we get a better approximated value for a definite integral, that is a to b fx dx, and that is the value for definite integral. Okay, when n tending to infinity. The converse of this is also true. That means if we have an infinite series of our form, then we can represent that sum as a definite integral. Okay. For example, let's take some particular cases. The first one is limit n tending to infinity summation from r is equal to 1 to n 1 by n f r by n. This is a limit of sum. We can also write it as limit n tending to infinity summation r is equal to 0 to n minus 1 1 by n f r by n. So now we can write this summation limit of sum as a definite integral, and that is equal to 0 to 1 definite integral fx dx. So how we get this? So basic idea, we take 1 by n as dx. Okay, r by n is replaced by x. So 1 by n, when we replace 1 by n as dx and r by n by dx, we get fx dx. And the summation signs, limit n tending to infinity, the summation is replaced by the integral sign. Okay, so we get integral fx dx. And to get this limit, we take the limit of n tending to infinity r by n, where when we take the starting of summation, that is r lower where we start r from 1 to n. So when we take limit of n tending to infinity 1 by n, we get the lower limit, and that is equal to 0. Limit of n tending to infinity 1 by n is 0. And when we take the limit of n tending to infinity r by n, r is equal to n, then limit n tending to infinity n by n, that is 1, and that is equal to 1. So we get the upper limit. So we get integral 0 to 1 fx dx. If we generalize this, so limit n tending to infinity summation r is equal to 1 pn 1 by n f at r by n is equal to integral alpha to beta fx dx. So here alpha is equal to limit n tending to infinity r by n is equal to 0. 1 by n is replaced by dx, r by n replaced by x, so fx dx. So basically x is equal to r by n, and we need to find the limit of x, that is limit of r by n. So when r is equal to 1, it gives you lower limit. So alpha is equal to limit n tend to infinity 1 by n, that is 0. So alpha is 0. And to calculate beta, the upper limit for x, beta is equal to limit n tend to infinity r by n. Here r is p into n. So p into n by n, and it cancel out, we get p. P is the upper limit for this summation. Okay. So my limit of sum is now changed to definite integral from alpha to beta fx dx. Clear? Okay. So just wait for a moment. Okay. So now we'll practice some question based on definite integral. So first question, the integral from pi by 4 to 3 pi by 4 of dx divided by 1 plus cos x is equal to, options are minus 2, option B 2, option C 4, and option D minus 1. Okay. So just need to evaluate this definite integral. So what is the method? First find the antiderivative for the function 1 by 1 plus cos x, and then apply the second fundamental theorem of integral calculus. That is, if phi x is your antiderivative, then what is the value of definite integral? Phi at upper limit minus phi at lower limit. Okay. So at first calculate the antiderivative and then apply the second fundamental theorem of integral calculus. Okay. So try. Okay, let's solve. So correct answer is option B, that is 2. So consider it as I. So integral I is equal to integral from pi by 4 to 3 pi by 4 dx by 1 plus cos x. To solve this, we multiply the numerator and denominator by conjugate of 1 plus cos x. That is 1 minus cos x. So we multiply by 1 minus cos x. So that is equal to 1 minus cos x by 1 plus cos x into 1 minus cos x. That is 1 minus cos square x on the denominator. Okay. Then the integral from pi by 4 to 3 pi by 4, 1 minus cos x and 1 minus cos square x is sin square x. So we get integral of pi by 4 to 3 pi by 4, 1 minus cos x by sin square x dx. So integral from pi by 4 to 3 pi by 4, 1 minus sin square x is cosec square x minus cos x by sin square x. So we get cos by sin cot x and 1 by sin x is cosec x. So we get integral of pi by 4 to 3 by 4 cosec square x minus cosec x cot x dx. So we have a formula, standard formula for this. Integration of cosec square x is minus cot x minus cosec x into cot x is plus cosec x. So we get the value of antiderivative. Now we substitute the upper and lower limit as the second fundamental theorem of integral calculus. So at first substitute the upper limit and then minus lower limit. So cot 3 pi by 4 is minus 1 and cot pi by 4 is 1 and cosec 3 by 4 is 1 by root 2 and cosec pi 4 1 by root 2. So substitute at in this value we get 1 plus root 2 minus 1 plus root 2 and that is 2. So correct answer is 2. Okay. Next question. So fx is a continuous function. Then which of these statement is correct? So option A, from minus 2 to 2 fx dx is equal to 0 to 2 fx minus f at minus x dx. Option B, integral of minus 3 to 5 2 times fx dx is equal to integral from 6 to 10 f at x minus 1 dx. Option C, integration from minus 3 to 5 fx dx is equal to integration from minus 4 to 4 f at x minus 1 dx. And option D, integral from minus 3 to 5 fx dx is equal to integral from minus 2 to 6 f at x minus 1 dx. So for option A, we can discard the options to check which options are correct. So for option A, if we take any even function, like the definition of even function is f at minus x is equal to fx. So according to the formula of even function, the value of integral is from minus a to a fx dx is equal to 2 times 0 to 2 fx. Okay, but for if here, if we take an even function, that is f minus is equal to fx, we get the value of 0. So we take any particular case of even function and we can discard this option A. So option is not correct. And for option B, C and D, we check a proper appropriate substitution to check which option is correct. Okay, so let's check. Correct answer is option D, that is minus 3 to 5 fx dx is equal to integral of minus 2 to 6 f x minus 1 dx. And since f is continuous function, so let x is equal to t minus 1 as substitution. So we use substitution method to solve this integral. So when you differentiate this, dx is equal to dt. Now we check the each option. So when x tends to minus 3 to 5, as in the case of definite integral, when we apply the substitution method, we also need to change the limit according to the new variable. Our now t tends to minus 2 to 6 because t is equal to x plus 1. So my integral minus 3 to 5 fx dx become x is equal to t minus 1. So when we replace, we get minus 2 to 6 ft minus 1 dt. Okay. Now the property of definite integral, because it's, and that property is whatever the variable, the definite integral always same. So just replace the variable by t by x, so we get minus 2 to 6 f x minus 1 dx. Okay, so which option is correct? Option D. Next question. So the integral from 0 to pi by 4 under root 10x plus under root cot x dx is equal to, options are root 2 pi, pi by 2, option C pi by root 2, and option D 2 pi. So I will give you a hint. So how will we solve this? We can write 10x as sin x by cos x and cot x as cos x by sin x. Okay, then simplify a little bit, and after simplifying, use the trigonometric identities to solve this. Okay, so as a hint, change 10x as sin x by cos x and cot x by cos x by sin x. Okay, so try. Okay, so let's solve. Correct answer is option C, pi by root 2. So let I is equal to integral 0 to pi by 4 root under 10x plus root under cot x dx. So as a hint, as I give you, just change 10x by sin x by cos x and cot x by cos x by sin x. So we get root under sin x by cos x plus root under cos x by sin x. And when we add this, by taking the common denominator, we get 0 to pi by 4 sin x plus cos x by root under sin x cos x dx. Okay. Now we can write this denominator root under sin x cos x as just multiply by root 2 and divide by root 2. We get root under 2 sin x cos x, that is equal to sin 2x, and then add 1 and subtract 1 under this square root. As we know, 1 can be written as sin square x plus cos square x, and then we can write this as root under 1 minus sin x minus cos x whole square. Okay, So now to find this definite integral, we use the substitution method. We take sin x minus cos x as a new variable t, and when we differentiate this, we get cos x plus sin x dx is equal to dt. Okay, and when we apply the substitution method different integral, we also need to change the limit. So when limit is 0, then t is equal to sin 0 minus cos 0. Sin 0 is 0 and cos 0 is 1, so minus 1. So lower limit is now minus 1. And when x is equal to pi by 4, then t sin pi by 4 minus cos pi by 4. Both are 1 by root 2, so you get 0. So now my limit become minus 1 to 0. So I become root 2 minus 1 to 0 dt by root under 1 minus t square. Okay, and this is a special case, that is integration of dt by root under 1 minus t square is sin inverse t. So you get root 2 sin inverse t, upper limit is 0 and lower limit is minus 1. So apply this limit according to the second fundamental theorem of integral calculus. We get root 2 0 sin inverse 0, that is 0, minus sin inverse minus 1, that is minus pi by 2. So we get pi by root 2. So correct answer is option C, that is pi by root 2. Okay. Next question. Integrate 0 to 1 sin 2 tan inverse root under 1 plus x by 1 minus x dx is equal to, options are pi by 6, pi by 4, pi by 2 and pi. Okay. So there is a term in the integrand involving root under 1 plus x, 1 minus x. So what is the appropriate substitution for this? Okay. So use that substitution to solve this integral. So correct answer is option B, that is pi by 4. So let's solve. So consider it as I. So I is equal to 0 to 1, integral 0 to 1 sin 2 tan inverse root under 1 plus x by 1 minus x dx is equal to, consider it as integral of 0 to 1 fx dx. Okay. So we just consider this as 0 to 1 fx dx. So here fx is equal to sin 2 tan inverse root under 1 plus x 1 minus x. Okay. And now we take substitution as x is equal to cos theta. So fx become sin 2 tan inverse root under 1 plus cos theta 1 minus cos theta, that is equal to sin 2 tan inverse cot theta by 2, because we know that 1 plus cos theta is 2 cos square theta by 2 and 1 minus cos theta is 2 sin square theta by 2. So we get 2 to cancel out, we get cot square theta by 2, and so we get sin 2 tan inverse under root cot square theta by 2, that is cot theta by 2. We can write this cot theta by 2 as tan pi by 2 minus theta by 2, because we want to cancel this tan inverse. So we get sin 2 into pi by 2 minus theta by 2, that is sin pi minus theta. And what is the value of sin pi minus theta? That is sin theta. So this is equal to sin theta. We can write this sin theta as root under 1 minus cos square theta. As this cos is theta is x, so now substitute back the value of cos theta, that is root under 1 minus x square. So fx become root under 1 minus x square. So now my integral becomes 0 to 1 root under 1 minus x square dx, and this is in a special type, and this integral is equal to x by 2 root under 1 minus x square plus 1 by 2 sin inverse x. So just substitute upper and lower limit. Upper limit is 1 and lower limit is 0. So when we substitute this, we get pi by 4. So pi by 4 is the correct answer for this definite integral. Okay. Next question. If I1n is equal to integral 0 to pi by 2 sin 2n minus 1 by sin x dx, and I2n is equal to 0 to pi by 2 sin the power 2 nx by sin square x dx, where n is a natural number, then which option are correct? Option A, is correct? Which option is correct? Option A, I2 n plus 1 minus I2 n is equal to I1 n. Option B, I2 n plus 1 minus I2 n is equal to I1 n plus 1. Option C, I2 n plus 1 plus I1 n is equal to I2 n. And option D, I2 n plus 1 plus I1 n plus 1 is equal to I2 n. Okay. So let's solve. Correct answer is option B, that is I2 n plus 1 minus I2 n is equal to I1 n plus 1. Let's solve. To solve this, we find I2 at n minus I2 at n minus 1. And what is the definition of I2 n? That is 0 to pi by 2 sine square nx by sine square x dx. N is natural number. So I2n is sine square nx by sine square x, and I2n minus 1 is sine square n minus 1x by sine square x. So we get 0 to pi by 2 sine square nx minus sine square n minus 1x by sine square x dx. Now there is a trigonometric entity, that is sine square a minus sine square b is equal to sine a minus b into sine a plus b. So when we apply this formula in this entity, we get 0 to pi by 2 sine 2n minus 1x into sin x. Here the value of a is nx and b is n minus 1x. So a minus b we get x, that is sin x, and a plus b we get 2n minus 1x. So we get sin 2n minus 1x into sin x by sin square x dx. Now sin x cancel out, we get 0 to pi by 2 sin 2n minus 1x by sin x dx, and consider it is a I1 n. This is the definition of I1 n. So we get I1 n. So we get, when we substitute n as n plus 1, so we get, just replace n by n plus 1 to get the required, to match the correct option. We get I2 n plus 1 minus I2 n minus 1. So when we take n plus 1, we get n plus 1 minus 1, that is I2 n, is equal to I1 at n plus 1. So we just replace n by n plus 1 to match the answer. So which answer is correct? Option B. Okay. Next question. We need to find the integral from minus 1 to 1 fraction function, that is x square plus x minus 3 dx, where this curly braces x denote the fractional part of x, and is equal to, options are 1 by 3 into 1 plus 3 root 5, option B 1 by 6, 1 plus 3 root 5, option C 1 by 3 3 root 5 minus 1, and option D 1 by 6 3 root 5 minus 1. So how we will solve this? So what is fractional part? If we if we have a number like 1.253, then that 0.253 is your fractional part for that number. So we can write any number as a sum of this fractional part and greatest integer function, that is a box function. So if we have a number x, a real number, then x can be written as box function plus fractional part. Okay. So we have to find this integral, this fractional part of x square plus x minus 3 dx. Okay. So we know that if fractional part x plus n, we can, if we add any integer and subtract any integer on a fractional part, then this value doesn't change, is exactly equal to fractional part of x. So fractional part of x square plus x minus 3 is equal to fractional part of x square plus x. Okay. And then use the definition of, that is x equal to box function plus fractional part, then change this fractional part as x minus x function, that is x square plus x minus box function, that is box function of x square plus x. Okay. And after that we will use some properties of the box function. Okay. That is, box function is not a continuous function. We break this interval minus 1 to 1 as the point of discontinuity. Okay. And then integrate on each subinterval and then find the value of integral of box function of x square plus x on the interval -1 to 1. Okay, so try this question, take it as a homework and solve this question. Clear? So try this question, and if you have any doubt regarding this question, then connect with us on Zoom call. Okay. Okay then, thank you. I hope the lesson was helpful.
Hello students, in today's lecture we are going to learn about waves, okay, and this is theory part first. This is our disclaimer. If we talk about trend analysis according to last 5 years in JEE main exams, so we can say the overall weightage of this chapter is 1.94%. Alright, and if we talk about yearly question distribution, so we can say in 2023 question asked from displacement relation in progressive wave. Number of questions 1, and if we talk about their difficulty level, so we can say question was average. Similarly, in 2022 question asked from particle velocity and wave velocity, number of questions 1, and their difficulty level average. In 2021 question asked from again from a displacement relation in progressive wave. Number of questions 1, and if we talk about their difficulty level, so we can say question was easy. Okay. In 2020 question asked from vibration of string. Number of questions 1, and their difficulty level average. Alright, so these are the important concepts for the examination. Students, in today's lecture we will cover first wave motion. After that we will discuss speed of waves. Then we will learn sound waves. After that we will talk about a displacement relation for a progressive or harmonic wave. Okay, and last we will see principle of superposition of waves. Okay, so these are the concepts which we will cover in today's lecture one by one. So the first concept is wave motion. Here question arises, what is wave motion? So we can say wave motion means that energy is transferred from one place to another, but the particles of the medium do not move forward themselves. Instead, they oscillate or vibrate around their mean position. If we talk about an example, okay, so we can say suppose if you throw a stone into calm water, so ripples spread out, yes or no? But the water molecules only move up and down in their place. They do not move forward with the ripples. This means the disturbance propagates but not the matter. Okay, so here we can say sound waves also work on this principle, where air molecules vibrate and transfer energy among themselves, causing sound to propagate. Alright, next is longitudinal waves. So we can say longitudinal waves are those waves where the particles of the medium vibrate parallel to the direction of wave propagation. Okay, so we can say if the wave is moving forward, okay, look at here in this diagram, this is the direction of the wave. This arrow shows the direction of the wave. So here the wave moving forward, the particles also oscillate back and forth in the same line. Okay, same line means parallel to the direction of wave. And due to this oscillation, in some places in the medium, particles come closer to each other. Okay, look at here. So here in this region the particles are denser, it means high pressure region. Okay, and this term and this place known as compression place. Okay, and some places they move further apart. Look at here. Okay, so there is a this is the low pressure region. Okay, which is called rare fractions. So we can say when a wave oscillate, so there is a compression and rare fraction. All right. So in a way, these waves bring about changes in pressure and volume. These waves required a medium with volume elasticity to travel, which is why they can propagate in solids, liquids and gases, in all three. All right. So we can say sound waves are their most common example. Clear? So this is the all about wave motion. Second wave is transverse waves. So students, if we talk about transverse waves, so we can say in transverse waves, the particles of the medium vibrate perpendicularly. Perpendicularly means 90-degree. Vibrate perpendicularly to the direction of wave propagation. Okay. So look at here, look at figure. So this arrow, right arrow in forward direction shows the direction of the wave. Okay, and this up and down. This one is up and this one is down. This shows the oscillations. So from this figure we can analyze that the direction of wave and oscillations both are perpendicular. It means the angle should be 90-degree. Okay, and this causes up and down or side to side oscillation in the wave and forming crusts highest point. So when wave oscillates, it form crust. So this region is the crust, and second one is the trough, and the trough lowest point. Okay, and if we talk about an example, so we can say when you shake a rope up and down, the particles of the rope move up and down while the wave propagates along the rope. Yes or no? So transverse waves can easily travel in solids because solids possesses rigidity, which helps bring the particles back to their original shape. Such waves also form on the surface of liquids, like ripples when a stone is dropped in a water. All right. However, they cannot travel in gases. Why? Why they cannot travel in gases? Because gases lack shear elasticity and particles are very far apart from each other. All right. Clear? Now we will understand some terms related to wave motion one by one. So first comes angular wave number. Okay. So if we talk about the angular wave number, so we can say the number of the wavelengths that occur within a 2 pi distance is what we call the angular wave number or propagation constant. So it is mathematically represented by k, which is equal to 2 pi divided by lambda, and the unit is radian per meter. Why radian per meter? Look at here. So in numerator and in denominator, so 2 pi the unit is radian and lambda unit is meter. So we can say radian per meter, where lambda is the wavelength of the wave. All right, everyone. The second term is particle velocity. what does mean velocity? What does mean particle velocity? So when a wave travels, the velocity with which the particles of the wave oscillate is called particle velocity. This is not the velocity with which the wave propagates. If we consider a transverse wave, then particle velocity is the velocity of the particle that oscillates up and down. Okay, any doubt here? So the expression for particle velocity v is equal to dy upon dt. Okay, and we know here y is the displacement of the particle at any instant. So if we differentiate y with respect to time, we will get velocity. Okay, if we are given the relation for instantaneous displacement y, by differentiating y with respect to time, we get the particle velocity v. Okay everyone, the next term is wave velocity. So again here question arises, what is wave velocity? So we can say the velocity with which a wave or disturbance travels is called wave velocity. So the velocity of a transverse wave is given by v equal to distance traveled by wave divided by time taken. Okay. So firstly we will calculate here v. So v equal to lambda divided by t. Here lambda denotes the wavelength, capital T represents the time period. Okay. Now if we multiply and divide this by 2 pi, okay, multiply and divide by 2 pi, then 2 pi divided by t will become omega and 2 pi divided by lambda will become k. Okay, so we can write it here as the velocity of wave, which is equal to omega divided by k, or velocity is equal to frequency into lambda. Thus we have the expression for the wave velocity as omega by k. Okay, or other is nu into lambda. Nu is the frequency. Okay everyone. Next is differential equation of wave motion. So now we have an equation which is also called the wave equation. Alright, this is the differential form of the wave motion. So d square y upon dx square is equal to 1 upon v square into d square y upon dt square, and this is the differential form of the wave, and you need to remember this. Okay, any doubt? Speed of waves. So the speed of waves is divided into two types according to the nature of the wave. These are, first is the speed of transverse wave. Second we will learn after this. Okay, so if we talk about the speed of transverse wave, so we can say the expression for the speed of a transverse wave can be derived theoretically in solid and in the case of a stretched string. So if we talk about in solids, so the expression for the speed of a transverse wave for solids will be v equal to under root eta divided by rho. Okay students, so here eta will be the modulus of rigidity, which will depend on the type of material, and rho will be the density of medium. Okay, so let's assume that if we stretched a string, okay, so in that case in the case of a stress string, the expression for the velocity will be v equal to under root t divided by mu. Here capital T is the tension in the string and mu is the mass per unit length of the spring. Okay. Now if the string is hung vertically, so and capital M is the mass suspended from the string and R is the radius of the string and rho is the density of the material of the string and L is the length of the string. So then the speed of wave will be v equal to under root mg divided by pi r square into rho. And we know rho is equal to mass upon volume. Here volume is AL. AL means A is the area and L is the length, or we can say rho equal to mu divided by pi r square. Okay students. So this is the speed of waves. The second is speed of longitudinal wave, or we can say sound wave. So if we talk about the speed of longitudinal waves, then the best example of longitudinal waves is a sound waves. Alright, this means the direction in which the sound wave propagates, the particles of the medium also vibrate in the same direction. Okay, it means the vibration of the particle and the propagation of the wave both will be same. Now we will look at the expression for the speed of longitudinal waves in different media. So now consider the medium to be solid. Okay, then in that case the velocity will be v equal to under root b plus 4 by 3 into eta divided by rho. Here capital B is the bulk modulus, eta is the modulus of rigidity. Yes, good. And rho is the density of the medium in which the wave is traveling. Alright. And when we talk about v form a velocity in case of long rod, so we can say assume the shape of the solid is like a long rod. Okay, so when we say that say long rod, it means that one of its dimensions is very large. Yes or no? So here assume the length is very long and the width and height are very small. Then in this case the velocity of the wave will be v equal to under root y divided by rho, and here y represents Young's modulus of the solid material. Okay, any doubt? So when the medium is liquid, okay, then in that case the speed of the longitudinal wave will be v equal to under root b divided by rho. Here b is the bulk modulus of the liquid and rho is the density of the liquid. Now if we want to calculate the speed of sound in gas, then according to Newton's formula, the speed of sound in gas is obtained when we replace capital B with the initial pressure P of the gas, that is B equal to P. Okay everyone. So when the medium is gas, in that case the expression for the speed of solid will be v equal to under root P divided by rho. Here P is the initial pressure of the gas and rho is the density of the gas. Alright. Any doubt here? Varsha, VK? Clear, yes or no? All right. Now we observe some factors that affecting the speed of sound. Okay. So now we observe the effect of temperature on the velocity of a wave. So this is our first factor. So what difference does it make to the speed of the wave when temperature increases or decreases? Think about it. So when temperature increases, or we can say when the temperature increases, okay, so the kinetic energy of air molecules will also increases. This means that those molecules start vibrating more rapidly. Okay, so sound wave is a wave that propagates through the vibration of these molecules. So when molecules vibrate rapidly, they also transfer sound wave forward quickly, which increases the speed of sound. Therefore, in summer, sound travels a bit faster, whereas in winter, the energy of molecules is low. So sound travels a bit slowly. Okay, so with every 1 degree Celsius rise in temperature, the speed of sound increases by almost 0.61 meter per second. Okay, next is the formula for the speed of sound is V equal to under root gamma into R into T divided by capital M. So from this relation, it is clear that V is directly proportional to under root T. Yes or no? So we can write V2 upon V1 is equal to under root T2 upon T1. So velocity is directly proportional to the square root of T. T represents temperature. This means if we take two cases where the temperature was T1 and then become T2, and the velocity was V1 and then became V2, then V2 upon V1 is equal to square root of T2 upon T1. Okay. The next factor is effect of pressure for gaseous medium. Alright, let's see. So when the temperature remains constant, a change in pressure does not affect the speed of sound. Okay, this is very important point. It means if the temperature is constant, okay, then what will be the effect on speed of sound? So there will be no effect. The change in pressure does not affect the speed of sound. So the reason for this is that when pressure increases, the density of gas also increases along with it. Okay, so the speed of sound depends on two things, pressure and density, but they cancel each other out. Alright, so in the formula, pressure is in the number here. If we talk pressure is just pressure in the numerator, and density is in the denominator. Okay, and temperature is constant, and their ratio always remains constant. Remember this point. Therefore, pressure has no effect on sound velocity. Next is effect of humidity. So when humidity, or we can say moisture, in the air increases, the speed of sound increases. Okay, humidity means the presence of water molecules in the air. This is the definition. So the molecular mass of the water molecules is less than that of dry air molecules, nitrogen and oxygen. Therefore, when water vapor mixes with dry air, the overall density of the air decreases. Okay, so the velocity formula will we have p, we can say p by rho. This means velocity is inversely proportional to density. So if density decreases, the velocity increases. Okay, so longitudinal waves that produce the sensation of hearing in our ears, or more simply longitudinal waves that are audible, are called sound waves. They are classified into following categories: infrasonic, audible waves, and ultrasonics. So if we talk about infrasonics, okay, so we can say these are sound waves with a frequency below 20 hertz. Okay, human cannot hear them. And snakes uh, here snakes do not hear these low frequency sounds but detect them through ground vibrations. Okay, the second is audible waves. These are sound waves with frequencies ranging from 20 hertz to 20,000 hertz, or we can say 20 kilohertz. Humans can hear these waves. Okay, and third is ultrasonics. These are sound waves with frequency above 20,000 hertz. Okay, human cannot hear these either, but dogs, bats, and dolphins can hear and produce them. All right, so these are the infrasonics, audible waves, or ultrasonic waves. Displacement relation for a progressive or a harmonic wave. All right, so velocity of a wave is given as v equal to frequency into wavelength. Okay, so v equal to nu into lambda, and we know the formula of angular speed in terms of frequency. So we can say omega equal to 2 pi nu, and this is equal to 2 pi upon t. Here t is the time period, and when we rearrange these terms, you will be get omega in terms of we can say nu. So in terms of nu, so it will be 2 pi v divided by lambda. Okay, because here v equal to lambda, v equal to mu lambda. So the equation for a plane progressive or simple harmonic wave traveling along positive direction of x-axis, we can say is y equal to a sine omega t minus kx. All right, and when we rewrite this with v equal to omega by k, so it will be v equal to y equal to a sine omega uh, uh, outside, and in the remaining term is t minus x divided by v. Okay, So it will be y equal to a sine 2 pi by t into t minus x into t divided by lambda. So y equal to a sine 2 pi by lambda into vt minus x. Here maximum value of y is a, okay, and a is the amplitude. Then dy upon dt is equal to velocity of the particle. So it will be v equal to dy upon dt. So when we take uh, differentiate y with respect to time, it will be a omega cos 2 pi by lambda into vt minus x. All right. And for the maximum value, so it will be dy upon dt is equal to a omega, which is equal to 2 pi nu into a. Okay. Or we can say dy upon dt max equal to 2 pi va divided by lambda, where v is equal to speed. So from the equation v is equal to dy upon dt, which is equal to a omega cos 2 pi by lambda vt minus x. Acceleration of the particle will be d square y upon dt square is equal to minus omega square uh, a into sine 2 pi by lambda into vt minus x. Okay, so this is the acceleration. How we can say this is acceleration? Anyone? Please answer. Yes. Okay. Next is relation between phase difference, part difference, and time difference. So if we talk about phase difference, then phase difference is equal to 2 pi divided by lambda times the part difference. Okay, and we can say when two waves meet at a point, there can be a difference in their paths, difference in distance, which we call path difference, denoted by x. So due to this path difference, uh, we can say a phase difference phi is introduced between them. So to calculate the phase difference, we have the formula, that is phi equal to 2 pi divided by lambda into path difference. Okay, and this expression, the expression of the phase difference tells us how much phase difference will occur for a given path difference. Okay, here lambda is the wavelength of the wave, and if the path difference is a complete lambda, then the phase difference will be 2 pi, or we can say 360 degree. So look at here in the figure, there are two waves. Okay, and both wave, their position, phase difference will be different. Okay, so the path difference is same, it should be different. So phi equal to 2 pi x divided by lambda. So when we rearranging this in terms of x, it will be x is equal to phi lambda divided by 2 pi. Next is the relation between phase difference and the time difference. So phase difference phi is equal to the 2 pi divided by t times the time difference, that is t. Okay, so if we need to find it in terms of time difference, then we can write it as phi equal to 2 pi t divided by t. Okay, meaning phi equal to 2 pi t divided by t. Okay, so from this we can also find t. So t equal to we can say 2 pi divided by phi into t. Okay, since there can be a time difference between two waves, if we need to determine the phase difference from that the time difference, then will we use this relation. So phi equal to 2 pi t divided by t. So in terms of t, it will be t phi divided by 2 pi. Okay. Students, all these formulas are very important for the exam. So you need to just remember all. And if we need to relate the time difference to the path difference, then the formula becomes t equal to tx divided by lambda, where lambda is wavelength and t is the time period and t is the time difference. Okay. So t will be, when we rearrange it, t equal to tx divided by lambda. And what will be the expression in terms of x? So we can say in terms of x, it will be lambda t divided by capital T. Okay, everyone. Now we will discuss about principle of superpositions. So assume that two or more waves can travel independently. Okay. So in the same region or space. Then the resultant displacement of the every particle in that medium at any time will be equal to the vector sum of the individual displacements caused by each wave. And this implies that if one wave oscillates a particle in the medium causing a certain displacement, and at the same time another wave arrives at that location, it will also begin to exert its influence. So the combined effect of the both wave will act simultaneously on the particle, and this effect is determined by the vectorially adding their individual displacements. And this principle is known as principle of superposition of waves. So mathematically we can write y equal to y1 plus y2 plus y3. It means that the solution to the wave equation are added in this manner. Okay, y1 plus y2 plus y3 and so on. Next is interference of waves. So what is interference of waves? Everyone, tell me. The phenomena of interference is that when two waves which have the same frequency traveling along the same path meet each other, then they superimpose, and due to this superimposition there is a redistribution of energy in the medium. After this, a new wave is formed which is called the resultant wave. Okay. So suppose we have a two wave displacement equation. The first wave is y1 equal to a1 sine omega t, and the displacement of the second wave is y2 equal to a2 sine omega t plus phi, where phi is the phase difference between them. Then the resultant displacement will be the sum of these two. So we can write y equal to y1 plus y2. So when we add both, you will be get y equal to a sine omega t plus theta, where we can say a equal to under root a1 square plus a2 square plus 2a1 a2 cos phi. And if we want find out the phi, so the formula is tan theta equal to a2 sin phi divided by a1 plus a2 cos phi. Okay. Now we will discuss constructive and destructive interference. Okay. So we can say when two waves meet at a point and their phase is same, that is the crest of one waves meet meets the crest of the other wave, and the trough meets the trough of the other. Okay, then it is called constructive interference. Okay, for constructive interference, the phase difference between the waves should be phi equal to 0 degree, or an integral multiple of 2 pi, that is 2 pi n. Okay, in the case of constructive interference, the amplitudes of both waves add up, and the resultant amplitude is maximum. So A max is equal to A1 plus A2. Okay, this is the maximum amplitude. Second interference is destructive interference. So if we talk about destructive interference, we can say when two waves meet at a point and their phase is opposite. It means what? That is, the crest of one wave meets the trough of the other wave. Then it is called destructive interference. Okay. For destructive interference, the phase difference between the waves should be phi equal to 180 degree, or we can say an odd multiple of pi. So it should be 2n minus 1 into pi. Okay, everyone, any doubt here? If you have any doubt, please ask. All right. Now, in the case of destructive interference, the amplitudes of both waves cancel each other, and the resultant amplitude is minimum. So mathematically we can write A minimum amplitude is equal to A1 minus A2. Okay, and if the amplitudes of both waves are equal, then the resultant amplitude becomes 0. Okay, next is intensity. So let's talk about intensity. What is intensity? So we can say the intensity is related to the amplitude of wave. It means what? It means the intensity of wave refers to the average energy that passes per second through each unit area carried by the wave. Okay, so suppose there is a speaker here. Okay, and if we move further away, the intensity decreases. Yes or no? Because the energy spreads over a larger area, and because as we move further away, the amplitude also decreases. So now observe that intensity is directly proportional to the square of the amplitude, that is I equal to directly proportional to amplitude square. This means that if the amplitude of the wave is doubled, its intensity becomes 4 times. Okay. So from this equation, we can find the ratio of intensities of two different waves, such as I1 upon I2 is equal to A1 upon A2 whole square. Alright, and suppose we have a two waves. One is Y1 which is equal to A1 sine omega t, and other is Y2 equal to A2 sine omega t plus phi. Okay, so these two waves are interfering. Okay, so now let's assume that the intensity of the first wave is I1, and then I1 will be proportional to A1 square, and if the intensity of the second wave is I2, so we can say it will be proportional to A2 square. So if I1 and I2 are intensities of the interfering waves and phi is the phase difference between them, then the formula for resultant intensity is I equal to I1 plus I2 plus 2 into under root I1 I2 cos phi. Okay. So now observe, if we talk about a place where waves are interfering in such a way that we are getting maximum intensity, then for that value of cos phi should be also maximum. So the maximum value of cos phi is 1. We know this. So when the value of phi is 0, therefore I max is equal to I1 plus I2 plus 2 into under root I1 I2, which is equal to under root I1 plus under root I2 whole square, for phi equal to 2 pi n. Now if we need to find I minimum, okay, so a condition where both waves are meeting and destructive interference is occurring, then the expression for I minimum will be I minimum equal to I1 plus I2 minus 2 into under root I1 I2. Okay, how? The minimum value of cos phi is minus 1. Alright. So we can write I minimum equal to under root I1 plus under root I1 minus I2 under root I1 minus under root I2 whole square, for phi equal to 2n plus 1 into pi. Okay everyone. Next is power. So if P is the power of a sound source, then intensity follows the inverse square law with distance d. Okay, power means how much energy is being expended at a certain place every second. So when a sound source like a speaker produces sound, it spreads energy equally in all directions. So the total power P of the sound remains the same. But as the sphere grows larger, the energy spreads over its increasing surface area. So the surface area of a sphere is 4 pi d square, where d is the distance. Therefore, I, that is intensity, which is energy per unit area, is inversely proportional to distance d. Inversely proportional to square of distance d. Alright. This means that if you move twice a distance from the sound source, the sound intensity becomes 1/4. This is called the inverse square law. Okay. Mathematically, the formula for intensity is I equal to P divided by 4 pi d square, and P is the power of the source and d is the distance from the source, and 4 pi d square is the surface area of the sphere with the source at its center. So from this formula, it is clear that as d increases, d square will increases even faster, and consequently the intensity I will proportionally decreases. Okay, therefore the sound appears loud near the sound source and becomes faint when moving away. Okay, so from this relation we can say I is inversely proportional to d square. Okay everyone, any doubt? Yes or no? All right, so let's see, we here learned wave motion, the propagation of disturbances through a medium characterized by oscillations that energy transfer. Then we discussed speed of the waves, then sound waves, then displacement relation for a progressive or harmonic wave, then principle of superposition of waves. Okay. Now students, we will solve some practice questions based on these concepts. Okay everyone. So are you ready for the practice questions? And all the practice questions are very important for the exam because it builds your problem solving skill. All right. So please wait 2 minutes. Okay. Now students, we will solve some practice questions based on waves. Okay. And this is part first. This is our disclaimer. So here we will solve some practice questions based on waves. So our first question, which of the following statements are true for wave motion? Okay. So there are four statements. Statement A, mechanical transverse waves can propagate through all mediums. Option B, longitudinal waves can propagate through solids only. Option C, mechanical transverse waves can propagate through solids only. And option D, longitudinal waves can propagate through vacuum. So which of these statements is correct? Okay, please solve this question everyone. You need to try solve this question. After that we will provide the solution of this question. Okay, please solve. Which one is correct? So its answer will be option C. Mechanical transverse waves can propagate only in solids. So we know mechanical waves requires a medium with shear strength to propagate. This means that as the wave propagates, the particles of the medium move perpendicular to the direction of wave travel. Okay, to support this up and down or side to side motion, the medium must have the ability to be rigid, which we call shear strength. In solids, uh, particles are tightly packed, okay, and bound by strong intermolecular forces, which is why they have a definite shape and high rigidity. This is the reason why solids possesses a shear strength. Okay. However, in liquids and gases, particles move freely and the force of attraction between them is weak. Okay, so when a shearing force is applied to them, they start to flow and do not resist change in the shape. Therefore, they do not possess shear strength. Therefore, when we talk about mechanical wave, they travel in only in solids. Okay, and longitudinal waves are entirely different. In these, particles move parallel to the direction of wave propagation, creating compressions means high pressure region and rarefaction means low pressure regions in the medium. Now the important point here is this, that these compressions and rarefactions transmit energy forward. Okay, in solids, liquids and gases, particles can push and pull each other, which allows these compressions and rarefaction to be created. So this is the reason why longitudinal waves such as sound waves can travel in all three states of matter: solid, liquid and gases. So its answer will be option C. Okay, mechanical transverse waves can propagate only in solids. All right, everyone. Okay. Next question. Uh, a sound wave is passing through air column in the form of compression and rarefaction. In consecutive compression and rarefactions, given options: option A, density remains constant; option B, Boyle's law is obeyed; option C, bulk modulus of air oscillates; option C, there is a no transfer of heat. Okay, so here in this question we need to state which option is correct. Okay, so please solve this question and find out the correct option. Okay everyone, please solve, you have some time. After that we will provide the solution of this question. Okay. Which one is correct? A, B or C or D? Okay, Okay, I will give a hint. Okay, so air is a bad conductor of electricity. So which one is correct? Now answer the correct option. Okay, anyone? So the correct option is D. There is no transfer of heat. Okay, so when a sound wave travels in the form of consecutive compressions and rarefactions, there is a no transfer of heat occurs. So here option A is incorrect. Okay, because when a sound wave travels, density does not remain constant. During compression, air particles come close to each other. Yes or no? Which is why density increases in that region. And if we talk about rarefaction, so we can say uh, during rarefaction, particles move further apart, which is why density decreases. Thus, as a sound wave travels, density continuously changes. Okay, and if we talk about option B, so we can say this is also incorrect, because according to Boyle's law, if temperature is constant, then pressure and volume are inversely proportional. Okay, however, the proportion of sound wave is so fast that there is no time for heat transfer, which is why it is an adiabatic process, not an isothermal one. In this process, temperature does not change, does not remain constant. Okay, so during compression, temperature increases, and during rarefaction, temperature decreases. Therefore, Boyle's law is not obeyed here. Option C is also incorrect. Okay, because bulk modulus is a property of any medium. It does not oscillate with changes in pressure and density. And option D is correct. There is a no transfer of heat from rarefaction to compression to rarefaction, as air is bad conductor of heat, like electricity. Air is a bad conductor of heat, and time of compression or rarefaction is too small. Okay, so time is necessary for heat transfer, and there is a process is considered an adiabatic process where the net heat transfer is zero. Next question. A sound wave of wavelength lambda is traveling in a medium with a speed of v meter per second. Okay, enters into another medium where its speed is 2v meter per second. Wavelength of sound waves in the second medium is what? So, which option is correct? Option A lambda, option B lambda by 2, option C 2 lambda, and option D 4 lambda. For this, our main concept is that whenever sound or any wave travels from one medium to another, its frequency does not change. Only wavelength and velocity change. Okay, but frequency remain the same. Now solve this question. Which one is correct? A, B, C, or D? Tell me the correct one. Yes, this is the time of solving questions. Okay, everyone, please solve. Which one is correct? So the correct option is C. Okay. So we know frequency of wave does not change when going from one medium to another medium. Okay. So what will be the frequency in the first medium? So suppose the frequency in the first medium c by lambda. Since velocity is v and wavelength is lambda, so the frequency will be v upon lambda. Okay. So similarly, when we calculate the frequency in the second medium, it will remain the same. So f prime will be equal to v. Okay. So when we equate both terms, you will be get v prime upon lambda prime is equal to 2v divided by lambda prime. So when we equate both, you will be get lambda prime equal to 2 times of lambda. Okay. So C option is correct. Next question. When tension of a string is increased by 2.5 Newton, the initial frequency is altered in the ratio of 3:2. The initial tension in the string is what? Okay. So here in this string needs to be tension in this string needs to be calculated. Given options: option A 6 Newton, option B 5 Newton, option C 4 Newton, and option D 2 Newton. So which one is correct? A, B, C or D? Please solve this question, everyone. Yes, which one is correct? So the correct option is D, 2 Newton. Okay. Let's see the solution. So here we know the frequency is proportional to uh, square root of capital T. Okay. And here T is the tension. So from here we can write nu1 upon nu2 is equal to under root T1 upon T2. Yes or no? So just substitute the values. Okay. So we are given that the ratio of initial frequency and final frequency is 3/2. And when the string's tension is increased by 2.5 newtons, so 3/2 equal to under root T plus 2.5 divided by T. So squaring both side will result in 9/4 uh, equal to 1 plus 2.5 divided by T. Okay. So when we rearranging this and adding terms, you will be get 2.5 divided by T is equal to 5/4. So if we find the value of T, So we can say T equal to 2 newtons. 2 Newton. Okay. So D option is correct. Next question. The speed of sound in oxygen O2 at a certain temperature is 460 meter per second. The speed of sound in helium is in helium at the same temperature will be what? Okay, there is a four options. Option A 460 meter per second, option B 500 meter per second, option C 650 meter per second, and option D 1420 meter per second. So which one is correct? A, B, C or D? You have to find out the correct one. Okay students, please solve this question and tell me the correct option. So the correct option is D, 1420 meter per second. So the formula for the speed of sound, we know V equal to under root gamma RT divided by M. In this question, we are given two gases, oxygen gas, which is a diatomic gas, okay, helium, which is a monatomic gas. All right. So this means the difference will be in the value of gamma. So since O2 is diatomic, the value of gamma for diatomic gas, that is Cp upon Cv, is 7 by 5. So the speed of sound for oxygen will be VO2 equal to under root 7 by 5 RT divided by 32. Similarly, V speed for helium, it will be under root 5 by 3 RT divided by 4. Okay, for monatomic gamma should be 5 by 3. Now we will take the ratio of VO2 and V helium. So it will be under root 7 into 3 into 4 divided by 5 into 32 into 5. So when we solving this expression, you will be get 1420 meter per second. Okay. All right. Any doubt here? Next question. It takes 2.0 seconds for a sound wave to travel between two fixed points. When the day temperature is 10 degrees Celsius, if the temperature rise to 30 degrees Celsius, okay, so the sound wave travel between the same fixed point uh, in what will be the travel time of sound wave wave between same fixed points. Okay, given options, option A 1.9 second, option B 2.0 second, option C 2.1 second, and option D 2.2 second. So students, tell me which option is correct. Okay, please try to solve this question. After that we will provide the solution of this question. Okay, these questions helps you to understand the concept and build your problem solving skills. So you need to try individually. Please solve this question, everyone. Which one is correct? So the correct option is A, 1.9 second. Okay. So let distance between two fixed points be D. Okay. Then we know that time equal to distance upon velocity. Also V is directly proportional to T, under root T. Okay. So when we substitute this, time will be inversely proportional to the square root absolute temperature. So it will be T1 upon T2 equal to V2 upon V1 is equal to under root T2 upon T1. So just substitute the values and you will be get the T2. So it will be 1.9 second. This means answer A is correct. Okay. Next question. A wave equation is given by y equal to 4 centimeter sine pi into t by 5 minus x divided by 9 plus 1 by 6. Okay. Where x is in centimeter, t is in second. Which of the following is true? Given options: option A lambda equal to 18 centimeter, option B v equal to 4 meter per second, option C A equal to 0.4 meter, and option D f equal to 50 hertz. So what will be the approach for this? The wave equation given to us in the form, we will compare it with the standard wave equation. Okay, and after comparing it we will find the values and then see which option matches here. Okay, so please solve this question everyone. After that we will provide the solution of this question. Okay. Which one is correct? So the correct option is A, lambda equal to 18 centimeter. So the equation given to us is y equal to 4 sine pi into t by 5 minus x by 9 plus 1 by 6. Okay, let this is equation first. So now we will write the standard equation. So y equal to a sine omega t minus kx plus phi. Okay, now the next step is we will compare with standard equation. Okay, so here y equal to a sine 2 pi by t into t minus 2 pi by lambda into x plus phi. Okay, so equating equation first and second, we get a equal to 4 centimeter, and then frequency will be reciprocal of time period, so it will be 1 by 10 hertz, or we can say 0.1 hertz. Wavelength lambda equal to 2 into 9, which is 18 centimeter. So we know velocity is equal to f into lambda. So just substitute the values, you will be get v equal to 1.8 centimeter per second. Okay. So the current answer is lambda equal to 18 centimeter. All right. Next questions. A wave equation which gives the displacement along y direction is given by y equal to 0.001 meter sine 100 t plus x, where x and y are in meter and t is in time in second. Okay, this represents a wave. So given options: option A of frequency 100 by pi hertz, option B of wavelength 1 meter, option C traveling with a velocity of 50 by pi meter per second in the positive x direction, option D traveling with a velocity of 100 meter per second in the negative x direction. Okay, so we need to determine which option is correct. Please solve this question, everyone. Which one is correct? So the correct option is D, traveling with a velocity of 100 meter per second in the negative x direction. So comparing given equation with standard equation, y equal to a sine omega t minus kx plus phi. Okay. So from when we compare, we get amplitude a equal to 0.001 meter, omega equal to 100 per second, k equal to 1 meter inverse, and we know the frequency formula, mu equal to uh, 2 pi, we can say reciprocal of time period, so it will be 100 by 2 pi, so 50 by pi hertz, because omega equal to 2 pi nu, and lambda equal to 2 pi by k, as we know lambda equal to 2 pi by k. So just when we equate 2 pi which m, so you will be get a v equal to here omega by k. So just put the value of omega 100 in, uh, per second and 1 meter inverse, so it will be 100 meter per second. This means option D will be correct. A plus sign in the equation implies that the wave is traveling in the negative x direction, and when it is the form of omega t minus kx, then the wave travels in a positive direction. This is very important concept, everyone. Okay, next question. Which of these statements is not correct for a progressive wave? Okay, and if we are given this wave y equal to 4 sine 2 pi t divided by 0.02 minus x by 100, where x and where y and x are in centimeter and t is second. Okay, t in second. Okay, the given options: option A, its amplitude is 4 centimeter, option B, its wavelength is 100 centimeter, option C, its frequency is 50 hertz, and option D, its propagation speed is 50 into 10 to the power minus 2 centimeter per second. Okay, so we need to perform its calculation by comparing it with the standard equation. So which one is correct? Please solve this question, everyone. Which one is correct? So the correct option is D. Its propagation speed is 50 into 10 to the power minus 2 centimeter per second. Let's see the solution. Uh, if we compare this with standard wave equation, y equal to a sine omega t minus kx plus phi, then it comes out to be a equal to 4 centimeter and omega is equal to 2 pi divided by 0.02 per second. Okay. Upon solving this, we will get 100 pi per second. K will be 2 pi by 100 per centimeter, and so we can find the lambda from 2 pi by k, which will give us 100 centimeter wavelength. Now we know the omega, so 2 pi nu divided by 2 pi nu is equal to omega, so nu equal to omega upon 2 pi. Just put the values, you will be get 50 hertz, and velocity will be v equal to omega by k. So just substitute the values, you will be get 50 into 10 to the power 2 centimeter per second. Hence the option is correct. Okay. Next question. The equation of a wave on a string of linear mass density 0.04 kilogram per meter inverse is given by y equal to 0.02 meter sine into 2 pi t divided by 0.04 second minus x divided by 0.50 meter. The tension in this string is what? Given options: option A 4.0 Newton, option B 12.5 Newton, option C 0.5 Newton, and option D 6.25 Newton. So which option is correct? A, B, C or D? Please solve this question everyone. You have some time. All the questions are formula based, and wave equation, when we comparing both, you will be get the omega, t, time period, frequency. Okay, so these questions are very simple. All these questions are important, and when you practice again and again, it improves your problem solving skills will be improved. Okay. Which one is correct? Please solve this question. Yeah, A, B, C or D. This is the last lecture, last question of the today's lecture. So tell me the answer, everyone. Yes, Varsha, VK. Which one is correct? A, B, C or D? So the correct option is D, 6.25 Newton. So using the expression of the speed, V equal to under root T by mu. Here T is the tension in the string, and so T equal to nu V square, which is equal to nu into V square by K square. As we know, V equal to omega by K. So comparing the given form of equation with standard form, that is y equal to a sine omega t minus kx plus phi. So we have omega equal to 2 pi divided by 0.04 radian per second and k equal to 2 pi divided by 0.50 radian per meter. Okay. So just substitute the values, you will be get the value of t. So when we solving the expression, you will be get t equal to 6.25 Newton. Alright. So this is our correct option, D option, 6.25 Newton. Okay, everyone. Thank you for your attention. That's all for the today. In next lecture, we will learn more about the waves, second part, and their practice questions. All right. So that's all for the today. Thank you for your attention, everyone. Thank you.